Welcome everybody to this Royal Met Society meeting on the history of numerical weather prediction in the UK. We've got an excellent lineup of speakers. I'm going to hand you over to Brian in a minute, who will be giving the first presentation, and then we'll chair the rest of the speaker session, and then I'll be back to chair the panel later. But I've got a few slides just to get through some admin and a little bit about the Royal Met Society membership that I just want to get through first. So if you need any first aid help, Catherine on the registration desk is a first aider, and I think the two ladies on reception here in the building are also first aiders, so please speak to them. And we're not expecting any fire drill today, so if we hear alarm, it's for real. And there are two fire exits in here, one at the back, the door you came through, and we exit through the front door, and we also have a fire exit here which takes us out a different direction of the building, so whichever route I think is safest to leave. Programme, I won't go through it, but as I say, an excellent lineup of speakers, a good range of topics focusing on the history of NWP, and hopefully leading to a really interesting panel discussion at the end this afternoon. Okay, I've got a short video, lasts about 1 minute, just gives you an overview of the work of the Society.
So many conversations start with the weather, and so many answers are yet to be found. But it's when you make a connection, a physical connection, a scientific connection, a connection of interest, that's when the world can change and doors can open. Weather doesn't discriminate, and neither do we. There's been no greater time to unite in our passion for understanding weather and climate, and shaping the future of our world for the benefit of science and humanity. We may be over 170 years old, but we are not standing still. Our journals showcase the latest advances, whilst drawing on the past. And our members are some of the most forward-thinking people on the planet. We are an independent voice uniting communities. We connect students with mentors, climate scientists with ecologists, communicators with researchers, and photographers with meteorologists. And we connect everyone with the weather. Whether you are working in the world of weather and climate, or just have a curiosity about the world around you, we are here for you. Join us and empower future generations. Join us to learn something new. Join us on your career journey. Join us in our passion. Join us.
Yeah, so I know we've probably got lots of members in the audience, so I don't need to suggest you join. But if you want to find out more about the Society, if you're not a member and you want to find out more about membership of the Society, do come and catch me at the coffee break. There's lots of amazing stuff the Society does, whether that's support to academics, professionals and the amateur community who are interested in weather and climate as well. It focused on education in that video, just to give you one example. So there was a report came out today on the new curriculum in England, and we've been working really hard to make sure climate change and climate literacy is a key part of that. It's one of the 5 focus points. It didn't hit the news today. If you've seen the launch of this report on the news, there were other focuses, but it's one of the top 5, which we're delighted about, and we've been feeding into that for the last few months. And you also saw a comment about photography. So we run the annual weather photographer competition. We announced the winners, I think it was last week. So again, if you missed that, there's a lot of information on the website. Here are some of the images that were part of this year's final. But this is just a plug for our calendar. So all those images go in our calendar. There's a QR code there if you want to pre-order a calendar for next year. Okay, I'm going to hand over to Brian.
Thank you very much, Liz. I'd like to add my welcome. Good to see so many of you here. And I think it's going to be a really interesting afternoon. As you'll have seen from the programme, our talks focus mainly on progress since the launch in 1965. And we will conclude with a look into the future, which I think is probably more uncertain than at any time in the last 60 years. But to start, I'm going to give a brief overview of the events that led up to the launch in 1965. So, now this all happened, but I'm not old enough to have been there. It was a close run thing actually, because I I first got in touch with the Met Office in 1967, so I just missed it. But so I've relied, obviously, on both primary and secondary sources for my information. But I want to point out three that I've used quite heavily. First of all, on the on the left there, Mavis Hines' computer story, published in the Meteorological Magazine in 1981. Her recollections of the early days. In the middle there, Anders Persson's paper published in Metaps in 2005, in which he drew out a lot of the official reports and so on from the early days. And it's if you want to know more about what happened, I would recommend his paper. It's not perfect, it is his view, but nevertheless, it's got a lot of stuff in it. And then thirdly, on the right here, an unpublished manuscript that Sir John Mason sent me a copy of, remembering, so again, this is memory, remembering the early days of his involvement. So I'm going to start with L.F. Richardson. No surprises there, I suspect. But of course, the origins of NWP go back much further than that to the formulation of the laws governing the state and motion of the atmosphere, which is what, early 19th century, and to the program that Wilhelm Bjerknes set out in 1904 to use those laws as the basis for weather forecasting, essentially on the basis that the atmosphere was simply a shell of perfect gas on a spherical Earth, rotating Earth. And that therefore it should be amenable to the laws of physics as observed in the laboratory. Of course, Bjerknes then went on and looked at those laws, and he set up a research program to look into that. But it was an Englishman, L.F. Richardson, who actually decided to attack the problem head-on. Richardson joined the Met Office as superintendent of Eskdalemuir Observatory in 1913, not the obvious place you'd look for groundbreaking research on NWP. He'd been in the National Physical Laboratory for 10 years before that, solving a variety of problems by finite differences, so nonlinear differential equation problems. And during the next 6 years, firstly at Eskdalemuir and then as an ambulance driver in the First World War, he developed the finite difference equations for the atmosphere and then attempted to solve them. His forecast procedure required the completion of 23 computing forms for each time step. It was all done manually with a slide rule, and as you probably know, the result was disastrously wrong, 145 millibars change in pressure in 6 hours. A rather unfortunate result of many years of work. And recent studies have shown that result was due to the fact that primarily due to the fact that the initial conditions were not balanced. Fortunately for us, he did publish his results, so people were able to look at what he did, even though it didn't produce a good result. So the next step had... Oh, okay. Why is it not going on to the next slide? Okay. Let's try that one. No, it's because I've used the...
Should we just come out?
Yeah, that might do it. That'll probably be enough, actually. Oh, the reason is because I was scrolling the... yeah, that's what I should have done, of course. Whoops, I skipped one. So, the next major step forward had to wait until after the Second World War, and three things had changed by then. The observational coverage was much, much better because of the growth of aviation. The first stored program electronic computers had been developed, and Gustav Rossby had developed a reduced set of equations that only supported geostrophically balanced motions, and therefore the need to balance the initial state was removed. It was John von Neumann who decided in the States that meteorology was one of the first problems that should be attacked, and the meteorological input was led by Jules Charney. It's difficult to grasp the issues that they had to overcome in order to get this first forecast done. When they started in 1946, ENIAC actually didn't have a storable program. So they had to wait until 1949 when the stored program capability was introduced. But even then, to program, you had to connect, and you can see here the way that the programming was done. So it was like an old-fashioned telephone exchange. You had cables that connected plugs in a plug board, and that was how you programmed. It was for each step of the process, you had to set up that. Then you fed in some cards, and some cards came out. There were, 16 computational steps to each time step, and 7 of those used the ENIAC, and the other 9 we used a punch card tabulator, which either duplicated or shuffled the cards. And the first successful forecast was carried out in 1950. It took 2 weeks, which isn't surprising given the scope for error with all these stacks of cards that had to be shuffled around and so on. I believe that they were dropped more than once. There was keen interest in the UK in what was going on in von Neumann's group. And in 1948, the Meteorological Research Committee advised that the application of computational methods should be pursued in the Met Office by the acquisition of an electric desk calculator. And sort of following on from this, in 1951, Fred Bushby was dispatched on a course to learn how to use the EDSAC computer in Cambridge, and access was gained to the Leo 1 computer of J. Lyons and Company. I won't go into why they had a computer. You can ask me later if you want to. Early development of NWP in the Met Office was quite a small group. On the left there, you have John Sawyer. He was sort of the brains behind it. He produced the equations for the model. The lead for the work, if you like, the project manager, was Fred Bushby in the middle there. And most of the programming was done by a succession of junior female scientists. I've shown Mavis Hines there. She was the first, but she was followed by Vera Huckel and Claire Whitelam. And actually, they did most of the programming work to create the various parts of the operational suite. I think that's everything I wanted there, yep. So in 1953, the Sawyer-Bushby model had been formulated and programmed, and it was being tested on both Leo and the Ferranti Mark I computer at Manchester University Department of Electrical Engineering. Unlike the ENIAC model, this model was baroclinic. It was a 2-layer model, so it, in principle, could produce vertical motion, and if you really wanted to, you could infer where there might be rainfall from that, although, of course, it was a dry model. In her 1981 paper, Mavis Hines recalled that the Ferranti computer used cathode ray tube storage, which was very unreliable. So computations were repeated until the same answer was obtained twice. However, it was a much faster computer than Leo, so overall it made about the same amount of progress. She also recalled, since we needed to use the computer for several hours at a stretch, most of our usage was at night. and for some years we used the machine for 2 nights each alternate week. We stayed in a nearby commercial hotel made of several elderly terraced houses now happily demolished. Readily available treats were the sight of sunrise over Manchester from the roof of the computer room, or the exhilaration of coping with an old-fashioned Manchester smog in which the buses were led by a man on foot holding a flare. It was sometimes necessary to have a member of the party with sufficient athletic prowess to scale the wrought iron gate of the university in order to gain access to the computer building. She doesn't say who. I wish I knew. So that was sort of the first serious work. In 1954, following the publication of the initial results, the Meteorological Research Committee recommended the Met Office should have its own computer. But it wasn't until 1959 that a Ferranti-Mercury computer, known as Meteor, was finally installed at Dunstable. Having written this down, it occurs to me that 1959, I'm sure, was the year that they moved from Dunstable to Bracknell. So I'm a little puzzled by this, but there we are. It went to Dunstable. There are pictures of it. At the time, it was reported to be one of the largest and fastest in the country. It had 5,000 valves, 3,500 diodes, and could perform 3,000 floating point operations per second, 3,000 decimal sums, which is not bad considering that a human can probably only manage 1, maybe 2 if you're lucky. It now had floating point numbers, that was a big advance, and indirect addressing, so you could do do loops. So that was a big step forward too. In the intervening years, the model had been developed into an improved Bushby-Whitelam 3-level model, and all the other necessary bits of an operational suite had been put together. So the observation, decoding and checking, analysis, and output, and so on. So a suite was put together for a trial in early 1960. It lasted 18 months. Sadly, the computer was neither powerful enough nor reliable enough to be used for operations. So that was as far as that got until 1965, with the installation of the English Electric KDF-9, which was a much more advanced computer. It actually had high-level language programming using Algol, though the model continued to be coded in user code, the KDF-9 assembly language. It cost £500,000 in 1965. This was a transistor-based computer, and it could perform 60,000 floating point operations per second. The input was by paper tape, and for the following, I am indebted to Peter Rowntree. So he says, the computer was delivered on the 2nd of April and was fully operational from July 19th. Bit quicker than our most recent computer. Operational trials started on this machine on the 16th of August. That's operational trials of the model suite. And results for the first month showed substantial improvements in wind forecasts over the UK at all levels relative to Central Forecast Office products. These results led to an immediate proposal for operational running, which was accepted on October the 4th, with a target date of the 1st of November. B.J. Mason arrived on the 1st of October, so everything was well in train when he arrived. However, he recalled continued resistance from some of the directors who had previously been quite sceptical as to the ability of NWP to produce stable forecasts. This model was dry. It was on a rectangular grid of 47 by 41 points, covering most of the extratropical North Atlantic and Europe. So, shortly after the computer arrived, B.J. Mason arrived as the new Director General. He had an impressive reputation as a physicist, but he was also a man who believed in getting things done. Quoting from his personal memoir, soon after I arrived on the 1st of October, I became impressed by the fact that the experimental forecasts were systematically more accurate than the traditional forecasts based on extrapolation of time sequences of hand-drawn charts. Accordingly, I decided, against the advice of some senior colleagues who favoured a longer trial period, remember this was only a 1-month trial, that the model forecast would be issued twice a day from Monday, the 2nd of November 1965. The media were invited to witness this landmark and gave it unprecedented coverage both in the press and TV. Fortunately, the first forecast was excellent. Mason opened his speech at the press conference. Ladies and gentlemen, it gives me great pleasure to welcome such a large and distinguished gathering of the press to the Meteorological Office. Today is a landmark in the history of forecasting in the office, a history which goes back more than a century, because this afternoon you will see the production of our first routine numerical weather forecast by computer. And there it is. That's a copy of the original forecast. You can see that it was printed out, sort of zebra chart, but not quite. It's grid point values plotted on a chart, and then they've been hand-drawn. A copy of that was subsequently mailed out to everyone who received the daily weather report. And Mason certainly got his response from the press. Many pictures of Mason and reams of computer paper and the computer room, and lots of comments, and you can guess what they were like according to which newspaper they were in. Looking at that forecast in a little more detail, it is actually quite an interesting forecast. So if you look on the left here, the 200 millibar. So this is the verifying analysis. This is the computer forecast, and this is the Central Forecast Office forecast. And there isn't really much doubt about which is the better one. It really was a considerable improvement. It's not quite so clear at the surface because, of course, there's fronts and things. But in the subjective forecast, you can see the trough has been pushed through with the cold front, whereas the trough is back through Biscay in the objective forecast, which is actually where it was in the analysis. The trough was behind the cold front. So again, there are aspects of that are definitely better in the objective, the computer forecast. So, to conclude, by the time of this launch, John Sawyer had formulated a bigger and better model using the primitive equations with 10 levels and with moisture, with the aim of predicting frontal rainfall. This model was implemented initially, the research was carried out initially, I should say, on a 40-kilometre grid by Fred Bushby and Margaret Timpson using the Atlas computer at Harwell, and became operational in the Met Office in 1972. And before I let Terry take over, just a snippet from their research publication showing that actually it showed quite some promise early on in terms of its ability to predict large-scale rainfall. So there I will leave it, unless there are any questions of clarification. We have got time, have we? Okay, yes. We have got time for some questions of clarification.
I think we've got time for a couple of questions, actually. So we are recording, it's not live streaming, but we've got a microphone so that the recording can pick up the questions. So if you can wait for the microphone to come, I'll take one from Tim.
So you mentioned ENIAC, and of course we now know, now all the work at Bletchley Park was declassified and so on, that they built the Colossus computer, which, I mean, arguably wasn't as programmable as ENIAC, but nevertheless it was a computer. And the guy who's credited with that is Tommy Flowers, who was a GPO engineer, I think, originally. Now, I have a recollection when I was at the Met Office of Fred Bushby saying that he used to go to talk to Tommy Flowers.
Oh, right.
Now, I just wondered if you or anybody, because I'm kind of curious about that connection, and I just wonder if...
Flowers go to Manchester?
Possibly, I don't know.
I think the Ferranti program at Manchester built on his expertise. I could be wrong.
Yeah, yeah.
But if that's
Yeah, that would be the connection. No, I'm just kind of curious to know because it's a sort of connection back to Turing in a sense, you know, which is interesting. Yeah. Thank you.
Incidentally, I came across a paper recently which suggests documented an American development in the war, which seems to have been quite parallel to Colossus, and that also had a sort of a quasi-stored program capability.
Yeah.
So all sorts of things creep out of work eventually.
Yeah. Thank you.
Time for one more. Yes, please.
Thanks for the great talk. So with the first computer model then, was it also faster than let's say the subjective, was it the interpolating method? Or was it just that it was more accurate that they decided to go with it?
It almost certainly was faster, but it's, but I couldn't give you exact timings on it. The forecast, in a sense, that the forecast process in the Central Forecast Office was driven by when the observations arrived and when the forecasts were needed. So they sort of took as much time as was needed between those two things. So in a sense, the subjective process, you can say, well, you could have done it a lot faster. It wouldn't have been as good, but it's putting a time on that's a little bit difficult. So far as I remember, the Met Office has always worked on the basis that the forecast should take about an hour. The computer forecast should take about an hour. I don't know if that was true in the early days, but I suspect it was of that order.
Great. Okay. Join me again in thanking Brian.
I got to misbiog because it was miscopied.
Yes. Oh.
Right, so I'd like to introduce Terry Davies, and I'm going to ask him to introduce himself because his biography, unfortunately, never got onto the webpage.
Yeah. Do I need to introduce myself? Yeah. I know nearly everybody here, I think, but obviously there are some people who have never seen me. But I'm Terry Davies. I joined the Met Office just over 50 years ago. And I worked at the Met Office ever since, apart from a short period off for good behaviour at ECMWF. And that was about 30 years ago as well. The plan of this talk is a whiz through 4 decades of NWP development and computing. There's many people involved in over 40 years. Several of them are in this room, and if I make any errors or leave things out, it's entirely up to me, not all the other people who were involved. And the other thing is, also noticing half the audience know quite a bit about NWP. This talk is for a more general audience, and so I hope you'll enjoy it. But one of the things about it is that I'll give some of the thinking we had when we were developing new versions of the model over time, and what we were aiming to do. But the first thing is just to make clear in NWP, it's more than just solving a set of equations on a set of grid boxes. And these grid boxes are more like pizza boxes. They're very thin compared with the horizontal dimensions. But it's as Brian had mentioned, the equations and the way we solve them, it's an initial value problem. And the crucial part of this initial value problem is that we need the state of the atmosphere at the start. And by the state of the atmosphere, I mean we need to know pressure, temperature, and the wind components. Well, mainly the horizontal wind components, because it's quite difficult to analyze the vertical motion, and water vapor, obviously, if we want rainfall. So on a basic model, that's what you need, and you need to know that at every grid box. However, there are far fewer observations than there are of these grid boxes. So you need a first guess of that forecast state for a start, and then if you've got observations, then you need to apply those observations to try and correct that first guess, and basically get this initial state. We also need to take into account a lot of processes that are not explicitly identified or treated in the equations of motion. There's a lot of other important physical processes involved with forecasting the weather, such as radiation, clouds, precipitation, interactions with the surface, and these we call physics parameterizations. Then the processing and the transmission of observations, the analysis, the computations, and the output all need to be done quickly, as that last question to Brian, how long did it all take? Well, the whole process, right from the beginning to the end, needs to be done pretty quickly. It needs to be done reliably, and you need to do it 24/7. So it's quite a big undertaking, being an operational NWP centre. And this is where Brian basically ended up with his introduction. This is the famous octagon domain. Again, some of you will recognize that when you joined the office. Octagon domain for obvious reasons. You'll notice that it basically doesn't include a lot of the tropics. It just about extends down to the tropics. It's on a polar stereographic projection. The octagon resolution is about 300 kilometers, and it had constant lateral boundary conditions and no flow across the boundaries. So it's basically a limited area model of a sort, without proper boundary conditions. And the forecasters used to refer to this as the coarse mesh, given the 300 kilometers, because the more important model, or the more important domain was, there's supposed to be,
It's down the bottom.
oh, is it down the bottom?
No, sorry, you were pointing down the bottom.
Oh, yeah, it's all right. Okay, it's the angle, so this area here, which was the rectangle, and again, the forecasters refer to that as the fine mesh, and that was 100 kilometer resolution. And now in this case, the lateral boundaries for the rectangle were provided by the forecast on the octagon. This dashed area is actually the verification area. Some of you might remember the famous Area 2 verification area, and I will show you statistics of the RMS scores for that area at various stages in the talk. So by the mid-1970s, the finite difference split-explicit scheme was introduced. That improved the efficiency of the model. There were precipitation processes on there, as Brian explained from the Bushby-Timpson model. There were surface exchanges, there were convective adjustments, there wasn't a deep convection scheme. Around about in the mid-1970s, I think the climatological radiation scheme was added. And then the analysis was basically a fit of observations that you had and a bit of basic quality control. And later, that fit was improved by a different analysis scheme called the polynomial analysis. And actually, even at that stage and the subsequent models, the basic requirement was that the 24-hour forecast should take 7 minutes. 7 minutes for the 24-hour forecast. Obviously, the analysis would be before that, and then the products and output, but I think it was actually less than 7 minutes. That was the requirement for the next model. So here's a snapshot of the scoring of that area 2 for the root mean square PMSL error, 12-month running means, and gradually more of this will be revealed as we go through the talk. And this is where we were by the end of, by 1981, 82, something like that. And those are the forecast scores. So basically, back here, it's almost like the man, and then gradually it's the man-machine mix. Because the PMSL was still kind of adjusted quite a bit when they produced the forecasts, and then it wasn't taken directly from the model. The gridded forecast chart was then verified in those early days. And that purple line, by the way, is the T+72 persistence error, which you'll see on the future graph. Oh, and I guess you'll see that there wasn't a big improvement in the model scores initially until just after I joined the Met Office. Ooh.
Press that button again. Whatever you press, there you go.
Okay, where next? So while towards the end of the 70s, we were now looking towards the next computer upgrade. So the early 70s was the 36195, and then we were starting to look at the first vector computers coming along in around about 1980. Of course, this is also the time when ECMWF was set up, and they too were looking to get their first computer at ECMWF. So we were in the business of looking for something that would, with a lot more computer power. And the machines we were looking at were now capable of something like 100 megaflops. So, as Brian explained, flop is a floating point operations per second. And actually, even all this time later, 50 years later, I still think 100 megaflops is pretty mind-boggling. And when you think we're talking about teraflop machines, yeah, but it's just I mean, just saying a megaflop is still mind-boggling that machines can do it that quickly. And this machine that we eventually got had 1 million words of 1 million 64-bit words of memory. So this compared with the 32K, I think, of the KDF9, and not a lot more, I think, on the 36195. Anyway, so the task and I used we a lot for all the people who worked on all this development at the time. So yeah, that's what it means. But so the first thing is we had to choose a design for a global dynamical core and analysis. And the first thing we did was to subjectively assess all the various models around and try and come to a conclusion, what were the important ingredients for a successful short to medium range prediction model. And by the way, back then, medium range meant 2 or 3 days, not 5 to 7 days. We felt, looking at all the different models and all the different schemes that were run, there were no clear advantages, signals between finite differences. Spectral models were still in the very early days, as were finite elements back then. So finite differences were by far the most widespread used method in the mid-70s. So we wanted to choose an efficient scheme to take advantage of vector processing. And we ended up having a 2 time-level scheme, split explicit scheme as used in the 10-level model. And we were having a latitude-longitude grid terrain following model, so terrain following for the vertical grid. So this is a looking at the speed up of the various computers in the early days, and again, this will extend over time. So we were looking at certainly 10 times computer power for the Cyber 205, which meant that global modelling was going to be a viable possibility. So this was the first global forecast model, which went operational in 1982, April 1982, the weekend after the Argentinians invaded the Falkland Islands. It went operational, a bit ahead of schedule. Fortunately, it had been pre-operational testing for several months before, so it was well on its way to becoming operational. But then the products had to be extended for the Southern Hemisphere for various reasons over that weekend. And I already said it was a finite difference scheme, spherical geometry, so now we were using a lat-long grid. And the global model, when we first introduced it, it was about 140 kilometers, so it's about double the horizontal resolution at mid-latitudes compared with the 10-level model. And this is what we use for the limited area model. So this is a section of the latitude-longitude grid, and we ran the limited area model on just a fraction of the global grid, and with boundary conditions supplied by the global model, and that is the limited area domain, still run in that form. And that had about a 70 kilometer resolution at 50 degrees north. In the model, we're starting to use a lot of the physics that had been developed by the climate group. Those of you who remember Meto 20, dynamical climatology, they were developing the physics schemes, obviously for the climate model, and if you like, they were much more advanced with the development of the physics schemes. And there was a lot of work going on to support the global Atlantic tropical experiment that took place in the around about the mid-1970s, about 76, something like that. 72, earlier than that, was it? Okay. And, you know, again, a lot of the experiences and working towards supporting that experiment came through on that. So now the radiation in this was interactive, and it used diagnosed cloud as part of the interactive radiation. And then later on, the gravity wave drag scheme was introduced into the model. I'm not going to say a lot more about the various physics schemes, so I hope I don't disappoint some members of the audience.
Just to say, it wasn't Meto 20 that the gravity wave drag scheme came from, it was Meto 13.
Yeah. So the other thing is, just to emphasize the other big difference, and again, okay, this was in Meto 20, was the data there was a lot more data assimilation development initially for the gate experiment that was going on in Meto 20, and then this moved over to Meto 11. And this is now the first idea of doing a data assimilation rather than just an analysis. And as Brian mentioned, getting balanced initial conditions was quite important. And one of the things that helps to balance the initial conditions is to add on the increments gradually through a time window. So you use these observations over a time window, typically about 3 hours, and you know, you do all the interpretation, the quality control, and the interpolation, and applying them, and then those increments are added to the first guess field over that assimilation period, and then the forecast is run. So there's quite a lot going on for this first global model. And how did it do? So now you can see quite a significant improvement in the forecast skills from the model, both at T plus 24, T plus 48, and T plus 72. By the time we get towards the end of the 1980s, there is a considerable improvement in all the on those forecast scores. And of course, I'm only showing here PMSL. A lot of other things, a lot of other fields were improved as well. And as Brian had mentioned in his talk, and the original motivation for NWP, aviation was a very important customer. And the aviation forecasts, even in the 1970s, were a big improvement of what could be produced, if you like, by the human alone. And that certainly translated down through the 80s. One of the things is we actually got a prize from some international energy thing for the amount of fuel saved by transatlantic airlines from using the latest forecast model. We're talking about millions and millions of pounds saved annually by the airlines by having more accurate wind forecasts. The other thing just to point out here, which might be a bit more controversial, when we get down to about 2 for the RMS, for the PMSL, that's really about the level where you need to be for it to be, for the deterministic forecast to basically be reliable. 4, it's not really very reliable. Day to day, you can get a different forecast, 24 hours ahead. This really, from a weather forecasting point of view, isn't really good enough. It's the best we could do, and the best we could do is with NWP, but nonetheless, you need to get down to about 2 in the root mean square error for the pressure for it to be reliable. And so certainly the 2-day forecast and the 3-day forecast, even they're greatly improved, they're still not that reliable. And to some extent, that's the motivation for doing ensemble forecasts. These kind of, at the longer ranges, the forecasts were not reliable enough. Almost as with all the development, as soon as you've got one operational and running, you're already starting to work on the next, looking ahead at the next computer and the next upgrade, the next increase in computer power, something like a factor of 10 again, and we actually the Met Office were going to buy an ETA 10, but before it got delivered, CDC, that part of CDC went bankrupt, and we ended up having to have Crays and YMPs, and we had 2 of them. But in fact, it didn't make a lot of difference to what we decided for the model development. So when we were looking at that, what we needed to think about was we had a lot more asynoptic data. There was a lot more data from satellites that we needed to process, study, and get that data into the initial conditions. The NWP and climate models were requiring more and more resources to maintain and develop. An NWP system, by the time you go operational, is more than decades of investment that you've put in full-time equivalents. 20 people for 10 years, is 200 full-time equivalents. And I guess you could argue the IFS has got thousands of years of resources put into it. You got more diagnostics required to inform development, reduce errors, and for products. So one of the decisions was made is we wanted to try and unify the dynamical core for the NWP, and the physics for the NWP and the climate model. So by the time we got the new machine delivered, or just after it was delivered, the unified, what we call the unified model for NWP and climate, went operational in 1991. There was a change to the analysis data assimilation scheme, so-called analysis correction data assimilation. As I mentioned, increasing the amount of satellite data to use, and we wanted to use them effectively. The model, we designed it as a deep atmosphere model. It was still hydrostatic, and we actually moved to a kind of a hybrid height coordinate for the vertical coordinate. We used the mass conserving finite difference scheme because that was a requirement from the physics. By this stage, incidentally, the physics development was now, the climate development was the Hadley Centre. The Hadley Centre had been opened and introduced. And the requirement for them was the climate model should be mass conserving. Then the global model, as it went operational, started off at about 90 kilometres in mid-latitude, and a small increase in the number of levels. We were still using a split explicit scheme. The limited area model, we'd been working on having a rotated latitude longitude mesh. So basically, whenever you have a limited area, you put the equator on the grid through the area you're interested in, and that way you get almost like a uniform grid, like a Cartesian grid over your area of interest, which is much nicer for the limited area model. And that went, that will keep on pressing the, that went to, that was at 17 kilometers resolution. And the other thing is, it was relocatable. You could have limited area models whenever you liked. And obviously, there were a few different areas that we ran limited area models for. So the climate model, or the physics, again, mainly developed by the Hadley Centre, and in 1984, the package was the HAD AM2 package, which included downdrafts, rapidly mixed boundary layer, and more cloud layers in the interactive radiation. And already, it had only just got operational, and then we were looking at our next computer upgrade, where we were starting to look at much more parallelization in the computers. We were starting development on 3D VAR and eventually 4D VAR, and the dynamical core we developed was the deep atmosphere non-hydrostatic equations in hybrid height terrain following coordinates. And we moved then to a semi-implicit semi-Lagrangian advection scheme. There was no operational requirement for kilometre scale NWP, but having a non-hydrostatic model meant we could experiment. So that's the timeline for the T3E towards the end of the 1990s. And then this is still the first unified model that went operational when we got the Cray T3E. So the main thing is an increase in horizontal resolution on both the global model and the what we call the UK mesoscale model. And the third climate version physics with more updates and more complexity to the physics, more advanced satellites. And in 1999, the 3D VAR went operational. And this is where we were by the time we got to the early 2000s. The error continued to decrease. Now we've got the two-day forecast, which has reached this the two line. So even the 48-hour forecast was now becoming more reliable. And on this now we're starting to score in the 4-day and 5-day forecasts. So here was the last set of computer upgrades, and what we call the new dynamics for NWP and climate went. The global model went operational in 2002. there was a further update in the physics, what called HAD-AM4, and 4D VAR came in 2004, and there was a MOSES, a surface exchange scheme, sea ice analysis, yet more data, starting work on ensemble prediction systems, which also led into ensemble DA, hybrid DA. For the global model, when it was introduced, the resolution was 40 kilometers at mid-latitudes. And then there was a larger domain, North Atlantic, rather similar to the first limited area model domain I showed before. The UK model was now down to 4 kilometers. In 2010, the horizontal resolution went to 25 kilometers, 70 levels. 4D VAR resolution was increased. Also in 2010, following that, there were other increases with the DA, and then in 2014, an update to the dynamical core and further increases on resolution. So this is where we got to by 2015. Now almost a T plus 72 is down to our 2 line, becoming quite a lot more reliable. And then, so that was the kind of where we'd got to back then with the global model. But as I mentioned, we were already experimenting with kilometer scale models, experimenting with 4 kilometer and 1 kilometer resolution over the UK and over Africa. There was the Boscastle storm in 2004, and at that time, Humphrey was experimenting with the UK4 model and showed that there were much better results when you with the 4 kilometer model than with the 12 kilometer model for things like the Boscastle storm. There were other flood events in that period. We started to experiment with an optional 1 kilometer domain over parts of the UK where the forecaster could ask for a 1 kilometer model to be run over one part of the UK. And then following the June-July floods of 2007, the Pitt Review recommended that a flood forecasting centre should be set up, and that was set up in 2009 in partnership with the Environment Agency. And in 2010, we went operational with a variable resolution UKV model at 1.5 kilometre model, and we were already experimenting with resolutions down to 300 metres. So basically, by about 2015, I'd already mentioned some of these. The 4-day forecast has the same level of skill as the 1-day forecast had in 1980. But one thing on these, on the forecast verification, the 1-day forecast basically had the same level of skill as the analysis had just 10 years before. So we could forecast 24 hours better than we could analyze the state of the atmosphere. And the 2-day forecast has the same level of skill as the analysis had in the early 1980s. And I think that is a kind of a much more important statistic, if you like, coming from the skill of the models. The high resolution models giving us much more detail and accuracy in rainfall, which is crucial for our main job at the Met Office, at least in the short range forecasting, of providing detail and confidence for issuing severe weather warnings. That's it.
Thank you very much, Terry. I think we have time for one question. Yeah, Alan.
Great talk, Terry. Fantastic historical analysis. I wanted just to raise perhaps a slightly controversial point. I mean, you've emphasised quite rightly how important the computer is in all of this, and the evolution of computing goes along with the development of the model. Of course, you could give the same talk and think about the development of the observational network over that time. You mentioned these things. It's not a criticism, but one could look at how influential the observations have been in terms of its development, the global observing system, etc. And also, you could look at the scientific understanding and knowledge of how the atmosphere works. And you talked about physical parameterizations, but not so much about, for example, academic research on teleconnections, on how the monsoon works, how stratospheric-tropospheric exchange works, and how that influenced the numerical weather prediction effort. And I just wonder if you'd like to make a brief comment about that latter part of how important the science itself was to the development, not just within the Met Office, but also outside.
Could I just interrupt, because I think we're going to deal with that question in the panel. So when we should get not just Terry's answer, but several. So thank you.
Yeah, and Alan, I ran out of time as it was, without mentioning all those things. But yeah, I mean, I agree, and we should discuss it later. I mean, that's,
we will. Yeah. Thank you, Terry. So now I'm going to invite Andy Brown from ECMWF. Andy since 2017. Andy's been the Director of Research and Deputy Director General at ECMWF. And prior to that, he spent most of his career at the Met Office working on the development of forecasting models.
Yeah.
Over to you, Andy.
No, thank you very much. A pleasure to speak this afternoon. So I thought to start just a handful of slides on ECMWF, just in case any of you don't need the organisation that does the best forecasts that none of the public have heard of, because we're behind organisations like the Met Office. So I think it started as a cost action in the early 1970s. And then here's some august people in 1975, it's our 50th birthday, setting up ECMWF. You can tell it's 1975 because it's black and white and there's a shocking lack of diversity. But now we're across 3 sites, so we're talking about NWP in the UK. I apologise for our Bonn and Bologna sites. But so now 23 member states and 12 cooperating states across Europe pooling resources. I think really at the start it was, as the Met Office and others were already doing the limited area modelling, have a first collaborative go at global modelling. And so we now have a shiny new data centre in Bologna. That's an artist impression of the new building at Reading University, but if I cycled past it this morning, it's looking not that different to that already, actually. It's going up very quickly. And that new building in Germany is currently a hole in the ground. So, I mean, I'm sure this is familiar to many of you, and Terry's touched on it, of course. Global observations, knowledge of the atmosphere, put it together in some kind of gridded or spectral model. I'm not going to go through showing lots of detailed results. I'll just point out a few landmarks on the ECMWF story and then show some of the long time series, a bit like Terry's, of sort of what that's all added up to, and maybe touch on Alan's point of what's contributed to it. So the first ECMWF forecast, it actually wasn't an ECMWF system. It was let's just collaborate or steal a model from the Americans, so a GFDL grid point model. So the first forecasts in 1979, 10-day forecasts using an N48. So by today's standards, very, very coarse. And it says at the bottom, only an atmosphere model. One of the things that's evolved a lot over time is the number of different components that are added, both to make the forecasts better and to increase the range of things that can be forecast. So through the mid-1980s, the ECMWF's own independent system, the IFS, was being developed, a spectral model, but without knowing Tim Palmer was coming, I'm pleased I put in a slide of the start of ensemble forecasting. So it was in there was experimental work going on before that, but I think ECMWF and NTEP in the States were some of the first to really go operational with ensemble forecasts. So initially, 33 members and about 200-kilometre resolution, running 3 times a week to 10 days. And actually, some of the sorts of outputs that are produced, you you'd still see these sorts of things today, you know, stamp maps, little maps of what these different members are just trying to, you know, it's not meaningful to do a 10-day deterministic forecast. You know, it's a probabilistic problem. So, yeah, probability plumes, probability maps, and I'll say more about how that's become even more central, the ensemble over time. I'm not going to go into the detail of this at all, but just to sort of echo the previous comments, you know, the data assimilation developments have been an absolutely huge contributor. You know, weather forecasting is an initial value problem. You haven't got enough observations, they're difficult to use. So I say I'm not going to labour the detail, but effectively it's taking the previous short forecast and the new observations and trying to do some optimal blend of those, going backwards and forwards in time to do the optimization. That sounds very dry, but it really, really matters to sort of how we take advantage of a lot. Yeah, we love all the new observations, they're absolutely crucial, but there's a science in how you use these observations as well. About the same time, the first seasonal forecasts. So now, of course, we're coupled to an ocean, so the first experimental seasonal forecast was in 1997. Did a very, very good forecast of the first El Nino event. I think this was possibly one of these occasions where we were slightly lucky. God, this is great, this system. And then, I think we're doing all right again now. And started experimenting with sort of monthly ensemble forecasting was already very much in experimental mode. And then by 2002 to 2004, we started operational monthly forecasts because there'd previously been, we had the medium range forecast out to 10 or 15 days and then the seasonal. So filled the gap with the monthly forecasts, again, coupled ocean and atmosphere together and fairly moderate resolution. I think this is the last slide. I mean, there's obviously all sorts of developments to the physics and details of the data simulation on the way, but this is the sort of our version of the resolution plot. So here's the different computers on time from 1980 up to the present day, and as Terry said, you know, sustained performance with a sort of unimaginable number of zeros of how many calculations these can do. But maybe just draw your attention to the solid line and the dashed line. So the solid red line is indicating the resolution of what we call the high-res system, so our one-shot deterministic forecast. You can see how it evolved from 210 kilometres in the early 1980s to 9 kilometres in the mid-2010s. We've been saying since about here that, you know, ensembles and probability is the sort of, yeah, the heart of what ECNWF does, but didn't really put our money where our mouth was because the ensemble resolution was always behind the high-res resolution until that cycle there. That was the Tim Palmer's one moment when the ensemble resolution caught up. So in a sense, there isn't a single standalone forecast. The ensemble runs a 9 kilometre resolution, so it's a 51-member ensemble running four times a day, 9 kilometre resolution globally. And this is just a pretty picture, actually. There was a famous case in the 2020s where there happened to be 5 tropical cyclones or hurricanes in the Atlantic all at once, which is very unusual. And this is the 2-day forecast for this. And that's not toggling over time, it's toggling over the 50 ensemble members. So I think you can, I hope you'd agree, you can see the 5 storms. I mean, I think it brings home actually just how far NWP has come, that you can produce something that looks so like a satellite picture, and you get a sense of, you can just see the exact positions of those tropical cyclones toggling around a bit, showing the uncertainty. So this is our, Terry showed plots very like this, but you know, improving accuracy. So this is anomaly correlation this time for 500 hectopascal height. So up is good on this plot. If you look at the blue, that's the 3-day forecasts. So the top of the blue is the northern hemisphere performance, and the bottom of the blue is the southern hemisphere performance. And so what's really striking is through the 1980s, most of the 1990s, the southern hemisphere is forecast very much worse than the northern hemisphere. And that's effectively because, you know, we've got a lot less aircraft and surface observations. Now in the 1980s, you know, we have a decent amount of satellite data, but we don't really know how to properly take advantage of it. And so it's the data assimilation developments, in particular the 4D VAR in the sort of late 1990s, that by and large, it's not quite true, but to a reasonable approximation, the southern hemisphere performance is as good as the northern hemisphere. And that's because the satellites don't care whether it's the southern or northern hemisphere. And in fact, in some ways, they're easier to use over the ocean because the radiative transfer is simpler. So southern hemisphere has caught up with northern hemisphere. This is the 5-day forecast. This is the 7-day forecast. And this is the much talked about day a decade improvement. So a 5-day forecast in 2020 is as good as a 3-day forecast was 20 years earlier. So what has made things better? And as Alan said, it's more and better observations. And sometimes it is just more, you know, more of the same satellites. Our systems are hungry for microwave satellite data, so sort of constellations of satellites are good. Sometimes it's more accurate. Sometimes it's measuring things we haven't had before. Of course, it's bigger supercomputers. I mean, resolution is maybe an obvious choice, but some of these things, what we do on the data assimilation, if we have a bigger computer, we can use the observations more aggressively. And I'd say the single biggest one is actually better science. If we just had a bigger computer and a big satellite, and nobody had come up with cleverer data assimilation algorithms, these forecasts wouldn't have got better in anything like the same way. I mean, it's hard to absolutely quantify the relative contribution of those. I think they're all quite significant. Some of the work we do, reanalysis, actually gives you some hints on the relative one. I would say probably the single biggest one is that. The way the likes of me spend a lot of time making cases for investments in infrastructure, but it's the people doing clever stuff with it that makes the biggest difference. So it's shown how forecasts have been getting better. As well as getting better, the range of things that's done has been increasing. So I've talked about from medium range and then doing sub-seasonal and seasonal forecasts. But we also do climate monitoring, so you can reuse modern NWSP systems to redo the analysis. In the 1985, we might have been a bit rubbish at doing an analysis because we didn't have the right science. We can redo it now with modern technology. Air quality forecasts, so putting more complicated representations of atmospheric chemistry, greenhouse gas forecasts and emissions estimates, flood forecasting, Terry talked about, wildfires. So more accurate, a bigger range of products. So this is just one prominent example. This is the reanalysis. So as I said, this is really just taking our modern NWP system and rerunning the last, well, I was going to say 40 years, but actually there's extensions back to the last 80 years or so. So here's a plot just showing the skill of the reanalysis. So here the computer isn't changing over time. The science isn't changing over time, but there are newer observations coming in as we go through. So those lines do slope upwards. So in a sense, to partially answer Alan's question, that line slopes upwards a lot less than the operational NWP system has, but the operational NWP graph had all three of my arguments. That's what happened. That's how much it gets better purely through the observations. And it's amazing again what these systems can do. We've got very little data back in the 1940s, but there was an extreme event that caused a lot of destruction in Portugal and Spain. And these systems are good enough at extracting information from the small amount of data we do have that it can do a plausible reconstruction that does agree. And huge value for climate monitoring. There's a huge academic climate community uses this. But what I'm going to come on to is this has found a new use in recent years as the heart of how people are doing these machine learning models. So the elephant in the room in terms of what happens next for numerical weather prediction. And I mean, potentially this is a Brian Mason moment where I don't think there's an uncertainty as to where this goes. So we've started in the last year running both a deterministic and an ensemble machine learning model. So effectively, what these models are doing, at the moment at least, they're taking traditionally produced initial conditions. So we're using the same data assimilation system we always use, and they're taking advantage of that reanalysis, which already encapsulates a lot of scientific knowledge, all the development that's been done in NWP. So we've got this 40-plus year gridded data set of the atmosphere every 6 hours. And these systems are learning just how to increment from one period to the next 6-hour period. And yeah, various tech companies made some sort of very strong claims about how good their systems were. We all said, that can't be true. Then we had a look, and it is a bit true. So, I mean, this is a deterministic, but I could show a similar plot for ensembles. So this is again looking at anomaly correlation for 500 hectopascal geopotential. So up is good. It's only 2002 to 2024 in this case. This set of lines up to that red one is the Eastern Rift line, are the physics-based models from the main global modelling centres. As you can see, everybody's been getting better. You know, we started, we could do a credible forecast for a 4 or 5 day range in 2002. Now we're up at about 6 and a bit days. So the physics, huge success of NWP. Those 3 lines there are the ECMWF machine learned model, and one from Google and one from Microsoft. So it's on the same graph, but they are, by this metric, and there are caveats, but for the large-scale performance, or if you want to predict tropical cyclone tracks, I think it's pretty much an objective fact that these models perform better. One very obvious concern with the machine learning models, and there absolutely are caveats with their performance and things we still need to understand, but it's often said that they won't be able to do extremes. And there are definitely limitations. I could come up, I don't know, there was a storm in Valencia that caused devastation a year or so ago, which was quite a local feature, and that these machine learning models, which are currently at coarse resolution, 30 kilometers, they missed that. So I'm definitely not trying to say they can do everything. On the other hand, here's a large scale. This was Storm Boris, which caused very extensive flooding in Europe. So the plot on the left is the observations. The plot in the middle is the IFS control. And the plot on the right is the AIFS, the machine learned model. Now again, it probably misses the very, very highest extremes over topography, but in terms of getting a very large scale, very severe signal, they do it. Maybe more striking and impressive, a year or so ago, this was at the time of the AMS meeting in Houston, there was very, very rare snow along the Gulf Coast. So this is what the physics-based model did. It understands physics. So it successfully produced snow on the Gulf Coast. Here's the machine learning model, which hadn't seen snow on the Gulf Coast in its training data set. It produced snow. So I think sometimes we think of these as sort of interpolators, or they can only learn from what they've seen locally. I think they're more physical than that. And I think that leads to my last slide, just sort of where's all this going? We publish a 10-year strategy every 5 years, and we were challenged by our member states to say, what does ECNWF look like in 2035? Thanks for that. So I just wanted to maybe talk about the top 2 ones. So the first one was innovating at the cutting edge of physical, computational, and data science. And so there was a statement that absolutely we need to be innovating in this data science, but the physical science still matters. Yeah, it may matter in a different way, but we need to be innovating in both. Delivering forecast tools and products of unprecedented quality. This was a very deliberately chosen phrase, exploiting data-driven methods anchored on physics-based modelling. So I think there's a statement there that, with our rather hazy crystal ball, we think it's likely that most real-time operational predictions maybe not all, but most operational predictions will be these machine learned models that run in a minute or two rather than the hour we were talking about, and are more accurate in many ways. But either for some products, some uses, for training data sets, for understanding, it anchored on physics-based modelling and scientific understanding remains important. So with that, I will stop.
I imagine there's a few questions. Yes.
So thank you for the lovely talk. My question is more about the recent developments in the AIFS. I want to know how much of the AI component, the model within the AI system, how much of it does it understand as physics versus just a regression of the physical trend?
Yeah. Well, as I tried to allude to, I think it's underplaying how physical it is to think it's just a regression. I say we've got numerous examples of it going outside its training data set locally. I mean, I showed the New Orleans snow. There were a huge flood in Dubai a year or two ago. The training data set had seen nothing like that, and it did it. Now, I'm not trying to say they're perfect, but I think there is so much physics encapsulated in the reanalysis that's used, all our science and our physics and our data assimilation and the observations. There's so much encapsulated in there, and I think the machine learning models are managing to sort of to learn from that.
And how much of the machine learning models use like explainable AI versus a black box?
There are efforts globally looking at explainable AI. We probably haven't gone very far in that direction. I mean, one thing that's quite nice for the weather prediction problem is we can certainly test very widely how well they're doing. You could say, I mean, the physics models have huge strengths, but we can only afford to test them on 6 months or 12 months of forecast when we're trialing an upgrade. We can retrain the AIFS and run 40 years of forecasts in a week. So I think we absolutely need to look more at physical consistency, what they're good at, what they're not good at. But I think the important thing for our community is to be open-minded. These clearly have a role, and we need to sort of nuance our understanding of what. But I do think this anchored on physics-based modelling, that we've got to be careful not to throw the baby out with the bathwater in terms of expertise.
Thank you.
Andy, thanks obviously for mentioning ensembles, but since we've got a slightly historical perspective, I want to suggest that the date that you put isn't correct about when ensembles were first operationally implemented. So in parallel with what was going on that Terry talked about at the Met Office, there was a parallel activity in Meto 13, which was on monthly forecasting. And Chris Folland, who's here somewhere, yeah, there he is, with David Parker, had developed actually what you would now call AI. I mean, these were basically statistical models for making monthly prediction. I joined the group in the branch in '83, and with James Murphy, who actually I was very pleased to see he won the Simons Medal this year, and Doug Mansfield. We were tasked with introducing the things like the 11-level model into this monthly predictions scheme. Now, Chris's empirical models were probabilistic, so it was kind of natural. It was almost a no-brainer that you would do it in an ensemble way. And in 1985, we started, and these were forecasts that were bought by utility companies, so they were real-time operational forecasts. So this is an operational activity. In '85 was the first time when we blended the statistical, pretty much like you're talking about now with AI, blended the statistical and dynamical ensemble-based models. So those were the first operational ensemble forecasts in '85. What happened when, I mean, you both Terry and you presented ensemble forecasting on sort of 5-day timescales as kind of obvious. But there was a lot of resistance to the idea at the time. And I think it kind of came from Charney, who coined this phrase, the limit of deterministic predictability. You know, and people say, well, it was around 2 weeks. So the implication is everything you do before 2 weeks is deterministic and everything afterwards would be probabilistic. And it took a long time to kind of disabuse people of that idea, that that was only an average sort of sense of predictability, not a sort of a day-to-day thing. And of course it took the famous, what we call the Great Storm, the Michael Fish Storm, to make people realise that things are not necessarily deterministic.
Going to the extreme, I
Yeah.
didn't mention it at all, but our data assimilation is an ensemble.
Yeah,
An ensemble
that's right.
Of data assimilation, so even
That's right.
to get
No, but I'm
finished,
saying there was a lot of resistance because people said, "Oh, just running the forecast 32 times originally, you could do other things with, improve your resolution or do something, And the forecasters didn't like it much either because they thought public would never understand probabilities. So, what you're sort of claiming now is okay. Yeah, it's obvious it should be ensemble based. It was very hotly disputed at the time. It took a long time for it to become kind of embedded. And I wanted to say something else, but it's now gone completely out of my head. But anyway, I think I've made the main point. Thank you.
I mean, as you saw, even NWP itself was disputed. In the early days.
Yes, that's right. I was interested when you said that because I kind of got the same
And if you look back in the late 50s, there was a real question as to whether the growth of error in the baroclinic growth process would be so fast that a 24-hour forecast was impossible.
Thanks. A very interesting set of presentations so far. Just interested to mention that I was actually started a job as a medium range forecaster in what was the old Central Forecasting Office, more or less having done a lot of short period forecasting, etc. But just about the time that we started seeing the ECMWF ensembles come in, and it was a real kind of paradigm shift. It was quite mind-blowing to actually see how forecasts actually diverged so dramatically, sometimes after just 2 days, but more often after 4 or 5 days. And it suddenly made you realise that the standard format of medium-range forecast, Tuesday will be, Wednesday will be, such and such, had to be just completely thrown away. And I think Tim's right there. It took a long time for ensemble to be accepted within the operational forecasting environment. But I think it certainly proved an absolute paradigm shift, certainly when I saw them first.
Oh, I don't have to take questions from ECMWF colleagues.
So yes, this is sort of historical meeting, and people have talked about the sort of drive for more computing power and resolution and so on. I just thought, sort of in a sort of retrospective question and what we've learned from the AI models, I just wonder whether in the past we kind of parameterized what we couldn't afford to resolve, and maybe the AI models have taught us that we should have parameterized what was not predictable. I don't know, it's just an interesting sort of thought.
I think actually many things have surprised me about the AI models. Probably the biggest one, actually, I probably complacently thought larger scales on the globe, it's well resolved, we know the laws of physics, our physical models will be best at the large scales, and AI might have a role at the small scales. That was one of many places where my intuition on AI was wrong, because actually the AI models are impressively good at the moment at the very large scales. What they can't do is give the local detail or the range of products that users want at the moment.
Okay, I think it's time to break. So welcome back. I hope you all enjoyed the break. To start off our second half, I'd like to welcome Dr. Tom Bendel. Tom is a senior scientist in the dynamics research team at Met Office, where he's been working since 2019. He's one of the main developers of the Met Office's new dynamical core, Gung-Ho. Prior to working at Met Office, Tom completed a PhD at Imperial College, focused on modelling fluids using finite element methods. Tom, over to you.
Thank you very much. I had forgotten I'd given you a biography, so my first slide is that all again. So I'm Tom. I guess Terry's given kind of the past perspective on development of NWP at the Met Office, and my task today is the present and a little bit of the future. Brian's already kind of given my biography for me. So I've been at the Met Office in the Dynamics research team for 6 years, and in that time I've mainly been building the dynamical core for the new modelling system, Momentum, and that's what I'll talk about mainly today. And it's actually a really odd time to give a talk like this in history for two reasons. One is kind of a simple reason, which is that the momentum model that I've been working on has been nearly delivered, so there's a question about what comes after that. And secondly, as we've already heard from Andy, and you're going to talk about in the panel discussion later, what's AI going to do? And Brian, you said something very similar to what I said at the bottom here. There's kind of this irony that even as our models are getting more and more certain in their predictions, the modelling itself is now actually very uncertain at the moment. And I've kind of, in preparing for this talk, I talked to Nigel Wood, who many of you will know, and he gave me a slightly doom-laden prediction, which was, oh, maybe you're the last generation of physics-based models. And I think that might not be a completely crazy suggestion in the way that it maybe would have felt 5 years ago. So, brief outline of the talk. The first part is going to be a kind of explanation about where the momentum model has come from, and then I'll talk about the momentum model in detail in the middle, and then touch on the future with AI at the end. We've seen from both Andy and Terry that one of the main ways that the model has improved over the last 60 years has been by increasing its resolution, allowing you to resolve more and more fluid processes. And as many of you will know, each time you try to halve the grid scale, this comes with a huge cost. I've written 8 times, maybe it's 6 times, maybe you don't quite need to halve the time step, but you're getting a square of the number of grid points. And the main way we've been able to do this is by having more and more powerful computers. And throughout the last few decades, a lot of this power has come from the actual improvement of single chips. So this is a plot here of various different chips and their performance over the last few decades. And so this is a logarithmic scale, and many of you all have heard of Moore's law, which talks about how every couple of years the performance of a single chip would double. But we've known for a while, and you can see this last decade, this performance has been tailing off. So you can't really rely on just the chips themselves giving you the increased performance. And actually we saw from, I think, both Terry and Andy's talks that lots of those supercomputers had more and more processors as they were going along. And now this is the predominant way that we expect to get a more powerful supercomputer, by having more and more chips and packing them together more efficiently. But this will only give you a better model if you can actually exploit it. So here's a plot. I was actually wondering if Terry might have something like this. So it's nice that you didn't actually in this case. This is a comparison of the new dynamics and endgame models and their speed, or time to run a weather forecast, when run on different numbers of processors. So this plot is, I think, from about 15 years ago, and was basically the motivation for the endgame model was that not only was it quicker, but New Dynamics had this tail here, where when you give it more processors, you weren't able to get a quicker result, whereas Endgame was better able to exploit that. But you can still see that this tail is such that you're not going to be able to then throw another double number of processors and get half the speed. So this is kind of a bottleneck in scalability. And this then is going to limit whether we're going to be able to get to a higher and higher resolution. So why is this scalability bad? And essentially it boils down to the mesh. So the latitude-longitude mesh has points clustered at the poles. So with our 10-kilometre global model at the moment, so that's 10 kilometres in the mid-latitudes, gives you a spacing of 12 metres at the poles. So that would mean that we would have multiple grid points in this room. That's crazy. And so if you have a fast wind at one of those grid points and a time step of 4 minutes, that gives you what's called a current number of 1,000. And this basically says that this grid point is trying to get information 1,000 grid points away. So you can have places that are geographically very close together, but really far apart in the computer's memory, and that really is a bottleneck to the data communication and being able to speed up the model further. That's what I just said. Okay, so this has been known as a problem with the latitude-longitude mesh for a while. I'm going to say 2010, but probably people recognize this before then. But it's been known that we wouldn't be able to get to higher resolutions because we were already at the limit of our scalability. And so this meant that when the next generation of even more powerful supercomputers came along, we wouldn't be able to exploit that power in getting a higher resolution model. So, to tackle this, we decided to move away from the latitude-longitude mesh to something that's quasi-uniform over the sphere. And there were a number of options that we could explore to do this, and lots of these take inspiration from sports. So, for instance, cubed sphere here is a bit like a volleyball, or you could go for hexagons and pentagons to get something like a football. One interesting mesh is the yin-yang mesh, which is kind of two latitude-longitude meshes spliced together but rotated a bit like a tennis ball. And I don't know if you count Dungeons & Dragons as a sport, but kind of an icosahedron is this 20-sided dice looks like this icosahedral mesh where you've got triangles. Okay, we chose to use the cube sphere. So this has 6 different panels, like a cube or a volleyball, and on each panel, the mesh is divided equally by the angle to the center of the sphere, which gives us quadrilateral cells, but where the lines aren't orthogonal to one another. This is really important, the lack of orthogonality, because the data structures that we use to describe different fields like wind, temperature, etc. in the model assumed or were reliant on that shape of the mesh. So in changing that, you've got to find a new way of representing your data. Secondly, a lot of the mathematical techniques that we used in the meta-offices model also exploited this orthogonality, so need a new method to solve those equations. And combining those two aspects leads to the momentum model, which is the next section of my talk. So the changes that come from changing this mesh, the implications for the data layout and for the mathematical techniques you need to solve the equations are so dramatic that they've prompted us to essentially start again. Not quite, but in large part. So our new framework is called Momentum, and you can think of it as the replacement to the unified model. And this has actually been an enormous endeavor, involving over 100 people for over a decade. So as I say, the early parts of the process, looking at what the different meshes could be and what the maths could be on those different meshes, began 14 years ago, and it's still not operational. So this has been a really, really long time, and as I'll come to with the AI, the environment around us has changed a lot in that time. So why did we choose to go to such great efforts? It wasn't just the scalability challenge that I've already mentioned, but a few other reasons which I'm now going to outline in the coming slides. So one of the things is performance portability. And the idea here is that there's now a more diverse range of supercomputers than there were before. So in particular, is your supercomputer CPU-based or GPU-based? And the way of exploiting those requires really quite different types of code optimizations. And changing the optimizations that you have in the code can be a really, really big piece of work. You've got thousands of files, hundreds of thousands of lines of code that have all of these parallel commands inserted into them. So the idea was to design a model that would be more easily able to move between different supercomputers. And part of that is because the Met Office's code isn't just used by the Met Office, it's used by many international partners who have different machines. So the way that we've done this is using a tool called Cyclone, and this starts my sequence of slides with interesting acronyms or names of things. So the PSY here stands for Parallel Systems. And this is a tool that's been developed by our collaborators in STFC. And this is like embedded in the Momentum code. And the idea is that it generates all of the parallel directives itself, rather than someone having to go through by hand and do it. And what this means is you can then move from one supercomputer with CPUs, say, to one that's, say, GPUs, and all you have to do is tell Cyclone, this is the command that you need to insert here. I've simplified that, but I'm seeing Andy's face, so I'm saying that. But that's the idea behind it. Second time we get to see Lewis Fry Richardson here. So another reason for starting again with the dynamical core is to improve the scientific formulation. So this is called ELFRIC, which is named after Lewis Fry Richardson. So this is another of our kind of funny acronyms. And there's lots of kind of improvements that are then part of this. So one thing is local mass conservation, which is going to be important for climate modeling, improved thermodynamics, improved stability. There's no special treatment required of the poles because there aren't any anymore. And a lot of this is embedded by having the same, a lot of the same nice mathematical properties that the endgame has, but taking them a step forward using a finite element model. I'm now going to slightly indulge myself by telling you about something that I've worked on in the last couple of years, which is the transport scheme. So this is the part of the dynamical core that essentially blows properties of the air from one grid box to another. So in dynamics research, we've developed a new scheme called SWIFT, which efficiently transports properties while conserving mass and preserving shapes. And yes, SWIFT is an acronym. It stands for Splitting with Improved Flux Form Semi-Lagrangian Transport. There we go, I managed to remember it. And here's a video that kind of illustrates the strengths of the SWIFT scheme. So this is a toy model where we've got these slotted cylinder type shapes that are then blown by a kind of a deformational wind out through the top right corner and then back in through the bottom left. And one of the state-of-the-art schemes, Cosmic, is mass-preserving and stable with long time steps, but it can't preserve the shape. So you get oscillations that create new minima and maxima, and these I've highlighted in yellow and magenta. And we've worked out how to get the same nice properties that the Cosmic scheme has in terms of stability and mass conservation, but whilst keeping it bounded between its initial values. And just in the off chance that a famous American pop star happens to watch the recording of this, if you have a spare invite for your upcoming wedding, I'm sure that my wife would be very happy to attend. Okay, another acronym, JEDI. This is the final then new aspect of the momentum system, and this is about data assimilation. So JEDI is the new infrastructure for processing observations to give the initial conditions. And this has been developed through the Joint Centre for Satellite Data Assimilation. And the idea is that this is going to be much more modular and flexible than our current observations processing system, with the idea that it can be more easily applied to different supercomputer platforms. It can incorporate new types of observation much more easily, and it has it will support an ever-increasing set of NWP configurations. And the data assimilation team really lean into the kind of the Star Wars nature of their JEDI acronym. So they've got lots of branding of their different teams like this. They even have like an internal email address that's called DARF. I saw a web page the other day that was named after Jar Jar Binks. It's crazy. Yeah, so those are the reasons why we've embarked on this really large project to replace our modeling system. Okay, so now I'll just have a few slides on the future and AI techniques. And I think it's fair to say that the last few years has seen really incredible progress in the development of these models. And it really is causing a revolution in terms of what modelling centres are going to have to do. And just to kind of illustrate some of this progress, I thought it could be helpful to have a timeline with quotes and papers that have kind of marked this progress. So I wanted to start with a couple of papers that came out at the end of the 2010s, where we were at the point where machine learning techniques had become quite mature and well known. And here are kind of a couple of papers which looked into the possibility of forecasting just using a neural net and data instead of having a physics-based model that solved equations. And at that point, these are quotes that I've taken from their abstracts or conclusions. They said things like, it's yet to be shown whether it could be competitive with physics-based modeling. And then you fast forward 3 years, and tech companies have published papers with models saying it's stronger than the world's best NWP system, or it's approaching state-of-the-art accuracy whilst being 5 orders of magnitude faster. And these are quite maybe alarming claims, or maybe exciting claims. And one that really captured, I think, the attention of my colleagues was GraphCast, which was published by Google DeepMind, which again had a similar kind of claim. They significantly outperformed the most accurate operational deterministic systems. And then since then, there's kind of been an explosion of different models. I could have fitted, well, I couldn't fit all of them on this screen, but there were lots to choose from, and I picked 2 that I think are quite interesting. One is the Neural GCM model from Google Research, which I think is really interesting because it actually contains a PDE solver inside the system, and it essentially replaces like the physical parameterizations with the machine learning approach, but still uses something that tries to solve the fluid dynamics equations. And a different one is Aurora, which is a foundation model, so it takes lots of different data sources rather than most of these models were trained on ERA 5 data. And then 2 kind of landmarks to show the kind of how this is being picked up by NWP centres. So Andy's already talked about AIFS, and the Met Office has recently published on the archive a preprint about its FastNet neural network model. So FastNet this time isn't an acronym, it's named after one of the areas in the shipping forecast. And this is the Met Office's graph neural network, which is similar in structure to GraphCast and AIFS, and it's been developed in collaboration with the Alan Turing Institute. I'm not someone who works on FastNet, so I'm not sure I'll be able to answer many questions about it, but it has a similar kind of structure to GraphCast and AIFS in that it takes an input of weather on a latitude-longitude grid and then predicts the state of the atmosphere in 6 hours' time by encoding that information on the grid into a neural network and evolving that. And I don't know whether I even need to say these things, but obviously the excitement about these types of models come from how many orders of magnitude cheaper they can be to run. And a lot of the reason for this, I think, is simply because they can take far larger time steps than physics-based models can, and they have considerably reduced complexity. They have many fewer variables that they're predicting. They show significant improvements over state-of-the-art operational physics-based models on many important metrics. And I think Andy was right to say that there's lots of caveats to that, but they are showing these improvements on those metrics. I've written some of my thoughts about things that are still questions. I think Andy maybe can even answer some of these things. One of these common things that people ask is how well do they do at predicting extremes outside of the training data? Something that I've thought over the last 3 years is that often you would come up with a question about these AI models, and then within a year there'd already be an answer. Someone's already developed an ensemble system, or they're already looking at how to develop climate-based models. But we're not at the point where these are although AFS is running operationally, we're not at the point that they've replaced physics-based models yet. So at the Met Office, we're now really looking hard at how to blend the benefits of traditional physics-based models with these AI-based techniques. And I just thought I'd give some examples of things that people are now looking into. So one of these is about nudging the physics-based model based on the output of an AI forecast. And as Andy mentioned, this is partly because of the large-scale motions look actually very good in the AI models compared with the fine detail that is actually quite convincing from the physics-based model. I've mentioned already the neural GCM model. We're looking in the dynamics research team. We're looking into similar approaches. And there could even be some quite straightforward ways of blending these models by, say, replacing a single component with a neural network that's been trained to emulate that. So this brings me to my last couple of slides, and kind of, I'm not even sure that this is my speculations, but it leads us to the question of where is progress going to come from in the future. So I think that physics-based models can still benefit from hardware improvements, scientific and algorithmic improvements, and improved observations. So we're not at the limit of the skill of physics-based models, but the efficiency and skill of AI models is so impressive that it's kind of started a revolution amongst Met centres about what their forecasting looks like. And so there is still a question about where the role of physics-based models is going to be in 5 or 10 years' time. Okay, so just to conclude, the Met Office has a new physics-based modelling system called Momentum, which uses a CubeSphere mesh for the globe, and that's scheduled to be operational in a couple of years' time. We've also developed a graph neural network model called FastNet with the Alan Turing Institute, and we're also exploring a number of approaches for blending these AI techniques with physics-based models. Thank you for listening.
Thank you very much, Tom. We have time for some questions. Yes, right at the back.
Thanks for a nice talk, Tom. I was just wondering if you can tell us about how the Met Office has responded to the kind of change in skills and knowledge that's required to this kind of more recent developments in AI. Are you training existing people? Are you hiring new ones? What's being done about it?
Both of those things. There has been essentially a reorganization program. So there had been kind of the informatics lab where a lot of expertise in data science had been developed. And as we've recognized how important this is going to be, the connections and links with the rest of the office have changed. So for instance, the team developing FastNet has earlier this year moved into dynamics research rather than being kind of out in a separate department. There's a lot of thinking, new roles of people who are really doing this thinking about what the systems in 5 years' time are going to look like. I don't regularly check the vacancies page, so I'm not sure how much hiring there've been. But we have been, reorganising essentially to address that.
Anyone else? Yeah, down the front.
Yes, a fascinating talk. You presented obviously a very strong case for the fact that the AI models are very much faster at producing a forecast than the equivalent physics-based models. But maybe my knowledge is out of date on this, but don't the AI-based models still require a physics-based assimilation scheme to actually generate the training data and the initial state, which then, of course, I understand DA is very expensive computationally. So are there any plans to go towards an AI-based assimilation scheme to replace, for example, like 4D VAR?
Yeah, that's a great question. I know that there are some groups around the world who are looking into end-to-end prediction system. So the data assimilation is kind of incorporated into that process. It just reads in some observations and gives you...
Including ECMWF.
Including ECMWF. I think that's probably the main answer. There's a question about, is that role of physics-based models actually now going to be in creating the data to train those AI models on, and it'll be interesting to hear kind of the perspectives from the panel later about that. Yeah.
Okay, thank you. It's very quick, including the microphone. When will Momentum be operational?
The current plan for Parallel Suite 49 is, I think, September of 2027 is the plan. But those plans can change. But yeah.
Okay, thank you very much. Thank you, Tom.
Thank you.
So now we switch tack slightly to a user of numerical weather prediction. Mona Luca has worked for ITV. Mona is head of Millbank Studios, based in the heart of Westminster. Studios support ITV's political and weather output. She leads a team of political correspondents, weather presenters, and broadcast engineers. Prior to her role at ITV, Manali worked for the Met Office, progressing her career from software programmer to business development manager. She graduated from Kiel in 1996 with a degree in geography and geology and completed a master's in information technology in 1997, specialising in GIS systems. She's also chair of ITV's International Ambassador Network and a member of the Council of the World Meteorological Society and a member of the Climate Ambassadors Steering Group. Thank you.
Thank you, Brian. Thank you, everybody. It's really good to see you, and this definitely is a bit of a gear change, I think, from the presentations that you've seen already this afternoon. And really, I'm here to just tell you a bit of a story. When I sat down to pull this presentation together, I realised the link between numerical weather prediction and TV weather broadcasting, and it's really quite closely aligned. And TV weather broadcasting is the area that I'm currently working in at ITV, but as Brian mentioned, I started my career at the Met Office in Bracknell initially, then moved to Exeter. I left in 2014 to move to ITV to basically head up their weather services. It was a service that Met Office provided to ITV, to various commercial broadcasters, but there was a point in time when they thought, you know what, we could just do this ourselves in-house. And so I moved across to help them formulate this little setup. I ended up taking quite a few meteorologists with me, I'm pleased to say, so it is very much Team Met Office at ITV. But yes, I think it's fair to say that we've seen a mutual evolution of NWP and television weather broadcasts, each pushing each other forward. So this presentation really is a celebration of how NWP models have supported and advanced TV weather broadcasting, transforming it from what was really largely observation-based to data-driven. And there's a lot of the content that you've heard in the presentations earlier that really do translate into some of the information I'm going to talk about. So as head of ITV Weather, I'm a consumer of NWP output, and in this presentation I'm going to run through the before and after and to see how NWP has helped drive TV weather forecasting and improved public perception and accuracy as a result. So as we know, before NWP, some of the information you've seen earlier, TV weather forecasts relied heavily on surface observations, satellite imagery, and human analysis from meteorologists. It was in 1954 when we saw the first televised television weather broadcast on the BBC, presented by George Cowling, all completely based on hand-drawn synoptic charts. At this point, the status of NWP was still theoretical. There was no computer-based forecasting as yet. But fast forward to a world with NWP, and forecasts evolved. Merging science and data, our capability significantly advanced with sophisticated computer models being able to simulate the atmosphere. By dividing the atmosphere into a grid, physics-based models running lots of times, given slightly different initial conditions and starting points, gave probabilistic insights, helping TV meteorologists to discuss not just what might happen, but how confident they are. And this extra context gave greater accuracy in our forecasts, allowing broadcasters to explain not just what the forecast would be, but also why. So you could say that television weather broadcasts provided a platform to showcase the power of numerical weather prediction, increasing public trust in forecasts. We've seen that this model output has driven forward the visualization of our weather as well. TV broadcasts now routinely show precipitation maps, animated pressure systems moving over time, temperature gradients, and air mass variations, all generated by NWP. And as NWP has advanced, it's delivering even greater high-resolution models. For example, the Met Office UKV at 1.5 kilometres, which has allowed more localised forecasts to be broadcast. So we've seen an improvement in relevance and accuracy for viewers. One additional benefit is that this forecast data could be automatically integrated and updated into broadcast systems. And this was a significant improvement from the hand-drawn graphics that we had in the past. So meteorologists and weather presenters spent less time manually creating their forecasts and more time analysing trends, preparing content, and engaging with audiences. In addition, we've seen an improvement in the communication of severe weather. TV forecasts have enabled us to quickly and widely disseminate weather warnings for severe weather to the public. Multiple model runs through ensemble modelling helped weather presenters to express confidence and uncertainty on air. Comparing model output, UKV, GFS, ECMWF, for example, allows broadcast meteorologists to compare scenarios. Presenters can now explain uncertainty, model disagreements, and confidence levels more transparently than they ever were able to before. The Beast from the East in 2018, the St. Jude Storm 2013 are just examples of warnings based on NWP, which were shared on TV days in advance. For Storm Eunice in 2022, NWP models gave days of notice for damaging winds, and TV broadcasts were able to warn the public effectively with specific timing and impact details. I remember that day I was travelling from Cambridge to London, and I absolutely altered my plans and my journey around the warnings that were issued. Even just a few weeks ago, the track of an incoming low-pressure system was uncertain, but it had the potential to deepen rapidly close to the UK. But as it turned out, it was named by Meteo France as Storm Benjamin, as impacts there were projected to be greater there. But the UKMO issued weather warnings for winds and rain, and we were able to actually, on air, explain to the public the two different scenarios that we had at play, and that really did help to enhance public safety and understanding on what the impacts of the weather were going to be. So what's interesting is that as we've advanced to our delivery and visualization of TV forecasts, we've of course set the bar even higher for accuracy. And public understanding has now grown so much, their expectations are incredibly high. So you could actually say that TV essentially drove the demand for better models, faster data assimilation cycles, which of course couldn't have been possible without more computing power. So TV has essentially helped justify investment in NWP research and development. One thing that's certain is that NWP has made TV forecasting much more visually engaging. Broadcasters moved from showing static charts to dynamic, model-driven visualization, only made possible by NWP output. NWP enabled time-lapse animations of data values, such as cloud, cover, rainfall, and pressure. It was suddenly possible to show how the forecast would change over time. It wasn't just a static one symbol on a map, but we were showing data hour by hour. It helped to convey to viewers that the weather was dynamic and evolved. So the benefit to our TV forecast was much more visually engaging graphics that are easier for the audience to understand. And from TV, we've seen this advance even further into digital platforms, which have not only enhanced the accessibility and the reach of NWP data, but also the expectations of instant availability and perceived accuracy. But I feel that weather presenters often serve as the face of these model-driven forecasts, adding human interpretation. During big weather events, we know that TV broadcasts still serve as a trusted voice and allow us to add extra detail and much more context to the forecast. So I'm going to finish by a bit of a summary that shows the kind of relationship and contribution that NWP has made to television, and in turn, the impact of television on NWP. NWP has provided accurate model-based forecasts. In turn, TV has driven the demand for accuracy and relevance. NWP has enabled visual storytelling, In exchange, TV has justified the investment in better models. NWP supports early warnings for severe weather. TV has pushed model developers to improve real-time delivery. NWP has enhanced the trust via science-based outputs, and TV has improved understanding of NWP concepts. So on this anniversary, let us celebrate the application of NWP alongside the history and success of television weather forecasts in the UK. Thank you.
Where was the question? Sorry.
So in the earlier talks, we've heard a lot about AI and how that's affecting the forecasting from the NWP point of view. So I was just wondering, how are you starting to see AI coming also into the TV world and the weather presenting, and how do you see that changing in the future?
Yeah, we're not seeing it so much in the weather presenting at the moment. We are seeing it in the TV world. We're using it strategically. In the news environment, we're very cautious about our use of AI. All broadcasters, I was saying to Liz earlier, I was at a conference in Edinburgh in August with the BBC and Channel 4, other broadcasters, and there is growing concern of misinformation and disinformation out there. So I think that the main UK broadcasters are definitely working towards, and already feel they have, but really trying to push the trusted voice, as the Met Office do in terms of our weather output. So that trusted news voice is something that's really key here. We're definitely moving and contributing a lot into the digital space. Attracting audience is a real challenge. As you can imagine, ultimately, there's fewer people watching TV now. It is very much a particular generation watching TV weather broadcasts, and so moving into that digital space is crucial for us to attract a younger audience. But of course, the majority will primarily use weather apps, and okay, they are improving all the time. But as I mentioned, you know, one symbol doesn't necessarily reflect the weather outside at that moment in time, and so that's why we still feel that the human presenter still has a role to play. But I think we're sort of working towards how are we going to continue to sort of push out content predominantly in that digital space, which I hope will maybe provide an alternative to an AI-based forecast that they'll naturally be getting on their phones at the moment. In fact, you can do any Google search, and just depending on the setup, you get a weather forecast as part of it. So it's just, and often that isn't necessarily a UK-based forecast, it could be from anywhere around the world. So it is a massive challenge for us.
Hi. First of all, thank you very much for the talk. My question is a bit more on science communication kind of thing, because your role is basically you are a communicator. Yeah. Given the trend of climate denial, all that kind of thing, have you noticed much of that mindset really seeping into your audience, your viewership, or even we know that news channels have their own biases, news agencies have their own biases. Do you really feel that seeps in there, or do you feel that meteorological forecasting is largely immune to this narrative, and why?
Oh no, I don't think we're immune to the narrative. I think we're really involved in the conversation, and a lot of our brilliant weather presenters, broadcast meteorologist Laura Tobin's a fine example, who almost on a daily basis, it's her mission to make sure she captures, climate content, reporting on the latest data, and we often pick up on the UK climate reports, etc. So she does, and most of my team do. The reality is you're probably just not watching it. Our regional presenters are fantastic, our regional output is fantastic, and we are so driven to tell the climate story, but we also do it in our news programmes. It's about the communities we serve, and a lot of our storytelling is around renewables, because everything related to climate reflects our economy, health, so we're doing that all the time. I mean, ITV, we're part of the Albert scheme. So we not only on screen, but off screen, all of our productions have to fulfill, you know, a particular set of criteria to ensure that we're delivering a zero carbon footprint as much as possible, or working towards that. But it also comes in the storytelling. I don't know if you watch Emmerdale or Coronation Street, you know, we're trying to normalise the conversation. We've done heat pumps in Coronation Street. There's just so much we are doing as a channel to embrace the climate conversation. I think it's important for us to take that responsibility. We do get the climate deniers. We did a full special on Anglia, the East Anglia programme on climate just a month ago, and no doubt we're going to get a few, you know, some pretty horrible individuals stating some horrible comments. And
Thank you for taking the flak, by the way, for all of us.
so I can go on because I'm so passionate about it.
Thank you.
Can you pass it down then? Thanks.
Oh, yeah, thanks. It's very, very interesting to see this. I think there's a bit of a reservation about these very, you know, nice cloud pictures that people, I'm sure you're aware, tend to focus on, you know, unpredictable details. So if you freeze frame on 3 o'clock tomorrow afternoon, people will say, look, there's going to be a shower at my house at 3 o'clock. So have you got any comments on that? Because in a sense, the old symbol sort of scenario was kind of less nice to look at, but more accurate, because you were just kind of saying there's going to be showers in that area. You know, so have you got any comments on that?
Do you know what? I feel that actually the public are getting both, because on your mobile phone app, it is still a very symbol-based delivery. And it's really challenging on TV, because the reality is we don't get the airtime. We have a short amount of time. You know, our biggest, longest bulletins, 2-minute 30, you know, if we're trying to convey the forecast, because you need to go forward as well. People need to make plans. So I can't just finish on tomorrow. I need to really think about the weekend, and that's what we're planning. So I think that actually the TV forecast has a purpose of serving a general overview to the public. If you're making decisions, you're planning something, you will then go and look specifically, whether that's at your mobile or, you know, if it's something even more you know, specific that you need the weather forecast, there'll be other ways in which you can get that detail.
Because, I mean, the app has the probabilities, of course, for
Yes.
rain. And a lot of people I know, admittedly, it's not a representative sample of the population, but do look at those and use those. So I don't know, is that something that that road you'd go down at some point?
We're definitely doing that, working with the Met Office, trying to introduce more, just changing the language and introducing more probability and probabilistic forecasting into the conversation. We do it now. You won't hear it nightly, but when we get those opportunities, when we're doing studio chats and we're putting more context, that's the time that we can do it, because again, in a minute 30, when you've got to give a forecast, you can't always get into that detail. I promise you we're doing it. You're probably just not watching.
Okay, thanks.
If I might, one of the things that strikes me is that when you're explaining a forecast or giving a forecast, the presenter has to have a sort of an understanding of what it is that NWP, what's the meteorology that NWP has come up with, and I think I wonder how much that's going to change if we go to AI-based models. So does the understanding come from practice, or does it come from understanding the physics behind it? If it's practice, then we can learn about AI. But if it's understanding the equations, then it'll be different.
Yeah. I'm kind of hoping it's the former rather than latter, and then it's got to be practice, because otherwise I think all forms of AI application in whatever industry you're in, that's going to just confuse everybody. I don't think everybody's going to be able to be ingrained into the detail of the actual, you know, yeah.
Do we have any forecasters who want to comment on that?
Please do.
No, perhaps not. Okay, thank you very much.
No problem,
Rona.
thank you.
So we have a good bit of time for our panel, which is good, because I think we're going to have a very interesting discussion. I'll hand you over to Liz to chair that.
Yes. So do we know how to switch the screen off, Abby? Because I'd like to get rid of the projector somehow. It will be, but I don't know how. Room controls. Shutdown system.
Very good.
Good. Okay. So we're going to invite some of our speakers, and I think Ben is joining us for the panel as well. So Ben Shipway is head of Dynamics Research Group and leads the scientific development of the LF-RIC, which we heard about from Thomas. So can I invite, I think, Mona, Andy, Ben, and Brian. Terry, you're not joining are you joining the panel?
I think Terry. Yeah.
Could we get another chair then, please? Yeah. So Terry, could you join us as well? So we've got about 40 minutes for this panel discussion. We're going to take questions from the audience. We've got one microphone for the panelists. Terry, come and join us when we get a chair. We'll go and grab one. And we've got a microphone roaming to pick up. As I say, we're recording this, so it would be good to just pick up the questions and the answers on the microphones. So if you have questions, please do raise your hand, and I'll try and get to as many questions from the audience as possible. So I think it'd be good actually, Alan, to kind of revisit the question that you posed at the end of, I think probably the second talk, I think it was, about the role of the importance of science, I guess, playing in the advancement of NWB, particularly with that kind of AI thread. So I'd just like to get the view, I think, from each of you. And we heard it in some of the talks, so I think we may kind of revisit some of those points. But I think the importance of science in that advancement of NWP, not just the supercomputing power. And I think it was your slide, Andy, at the end, kind of had the three elements. But I'd like to hear from our panellists on that. And Mona, I think from the science perspective, I think it would be good to hear about how we communicate that science, because there's a lot of complex science in there. I mean, I think it's important we can share that with a wider general public audience. So I'd be interested to hear your view on that. Terry, do you want to go first?
Well, it looks like I've been given the microphone to go first. So, I mean, one of the interesting things about the AI work so far, like a lot of these things, I mean, just like the Met Office press conference 60 years ago, there was a lot of hype in that. And there's been a lot of hype with AI. Tom put some of these things up, they say, well, AI is beating the deterministic models. Well, I mean, and they were writing that 2 or 3 years ago, and basically AI has not replaced the deterministic models yet. They're being used more and more, but they haven't replaced it. And the other thing is Andy's point about the caveats about on a certain measures that AI appears to be performing better. But what was noticeable, a lot of these measures are in the medium range, and basically, the Met Office, well, and actually the TV forecast. A lot of people are interested to know, is it going to rain today or tomorrow? Is there going to be severe weather today or tomorrow? And I haven't seen, I've seen very little AI that's targeted. I know there's a European project where they are looking, like we did for the limited area models for NWP, they are looking at AI for local weather and severe weather, but it's at a very early stage. So there's still a lot of work to be done for AI to be truly called weather forecasts.
Brian.
Thank you, Terry. I'm going to take a slightly different tack. When I talk to people in the operational team about where the accuracy comes from, there's a very strong push in some quarters to say that it all comes from better observations. But then they say, but of course it does depend on them being assimilated. So when we look at the improvements in the scores, the biggest improvements tend to come from data assimilation. So I go and sit on the data assimilation people and say, if we're going to improve our 6-hour forecast, we need better data assimilation. And what the data assimilation people come back and say is, yeah, the trouble is that the data assimilation doesn't get better unless the model correctly resolves the things that are being observed. And so that using the observations through the better data assimilation depends on having a better model. And that isn't, some of it's about resolution, but a lot of that's about the representation of processes. So it's all circular. And I don't think you can actually pick out one thing and say, you can't get the optimum result by focusing in one area. You've got to focus across all the areas, and they all depend on each other. And I'll leave it there.
From my kind of input into this question, it's really going to be that we want to protect the science, of course we do, but the communication is the critical thing and the interpretation of the public. But equally, they unfortunately are now growing in their expectations. They want everything immediately. They want more, faster. So I think that unfortunately we won't be able to continue as we are. We're going to have to embrace the future of AI. I just hope we do it in a responsible way. But the communication of it is the key thing I find, because when I left Exeter and you move into that world of TV land and people's understanding, and we do lots of audience research, and it's unfortunately it's just the reality that actually what we perceived as something that they'll understand, actually they don't always get that detail. So communication is really important when we deliver this.
Thank you. Andy?
Just going to come back to the science in the NWP models. I mean, just to give one example, the most valuable observations we have are the microwave profilers. But for many, many years, we only used those in clear sky conditions because the science wasn't advanced enough to understand how to interpret the signals when it was cloudy. Then it was 10 plus years of research, and people were asking questions. Should we give up on this? Is it just too hard? And going to what's called all-sky assimilation, where we use the microwave data in cloudy conditions, sort of roughly doubled the impact from the most valuable observations. And still, if you look at a map of how we use this data, we barely use it over sea ice or lots of areas of land surface because we don't know how to. And so, yeah, I'm delighted I've got a big computer. I'm delighted that satellite's there, but it's the science to exploit it that's needed to get the full value. And even if we go to the AI world, I think it's either in how you design the models or certainly how you evaluate them, what lenses you look through to see whether they're doing the right thing. That needs an understanding of how the real world works. And so, yeah, I think I'm quite radical on how operational predictions may well change. But I think we've got to be very careful to protect what we need under the hood in terms of understanding in our tools, and more particularly in the skills in our community.
Thank you. Ben.
So perhaps unsurprisingly, given the group that I lead, I'm going to say that so HPC improvements in that is where things have come from, but it's going back to, I think it was Andy's bullet point. It's the clever people that come into that process. It sounds like it's quite an easy thing to just get a faster computer and run your model at higher resolution. And as Tom showed in his slides, there's an awful lot that goes behind that. And so I think it's both the algorithmic development of numerical methods, and that goes across the models and data assimilation, but also the computational science that's required to actually get these fairly massive machines now to give you what, and that goes back to the small machines when they were relatively massive in their time. But having those clever people and those clever methods are really the way that we've been able to exploit both the HPC and then the science as well.
Okay.
Could I possibly
yes, please. I'll get the mic to you, then away you go,
Alan. If I can be controversial, which comes
please
naturally. I don't think any of you actually addressed the question of the science, although peripherally you touched on it. I remember vividly when I was a PhD student, which is a long time ago, there was a dialogue between the Met Office and, it was then Imperial College I was at doing my PhD, where there was regularly comments from the Met Office like, well, it's all very exciting, this ED model of baroclinic instability, that you're working on, but how has it actually changed anything that we do in the Met Office to predict the weather? And that message has stuck with me for a long time because, you know, a lot of the academic research in meteorology is about trying to disentangle how the atmosphere works. You know, how does the Indian monsoon affect the Mediterranean climate, for example? Or, you know, there's so many examples I could quote. And it's sometimes hard when listening to the modelers talk to see how that kind of knowledge gets into improvements in the physics or the models. But I felt very encouraged by Mona's comment where actually she's in the position where she has to, and I think it's really important, to be able to provide that kind of context, hopefully based on really good scientific understanding of how the atmosphere works. And one of my concerns about AI is that we may take the foot off the pedal of trying to continue that understanding, which is at the base really of trust. You know, why should I sort of remember also the famous GMO debate about, you know, the typical genetically modified tomatoes. That dialogue with the public was completely was completely messed up in this country. It wasn't communicated. The public didn't trust GMO organisms and produce, and actually the industry just died as a consequence. And I just worry that with AI, we might be in the same boat, that if we are not able to persuade the audience that we do have this underpinning scientific knowledge and understanding of why the weather changes the way that it does, not just how it changes, but why is it, that we may actually lose that trust with AI. So that was the sort of basis of my concern.
And that linked to my next question around trust. It was mentioned in a few of the talks, and I'm really glad you brought that up because, again, trust is important, both in the organisation, the model, the data, the communication, the person that's, you know, communicating it. Trust is front and centre throughout all of this, and not just with AI, but, you know, actually to gain that trust takes a lot of time and effort, and you can lose it, you know, overnight very quickly. So again, maybe a response to Alan's question, but I'd like to get a view from the panels about the importance of trust throughout all of this, whether it's NWP, AI, communication.
Maybe I'll
Yes,
very quickly
please.
start then. So thinking about physics-based models, there's an awful lot of work that goes on at the Met Office and other centres to properly evaluate those, to look at huge range of metrics, different processes. Some of the things that you're talking about, Alan, I think, so in the global model evaluation team and the regional model evaluation teams. And we've put a lot of effort into that over the years, and there's an awful lot of expertise there. One of the things that we're certainly trying to do at the Met Office is to make sure we can use that expertise appropriately with the AI models. They will be different, the way that we evaluate things, but there's an awful lot of expertise that we can bring to that. And I think that, as Andy said, with the AI models, there are still lots of questions. You know, we look at the broad metrics, and they're very good. But there's an awful lot that we can do, and we are starting to do, to try and unpick that from the expertise that we have in the physical models. I'll very quickly pass to Andy because I think he wants to say something. But specifically on the AI side of things, we are very worried about trust. And in our team, we have one person who is only one person at the moment, but they're developing the collaboration, certainly with ECMWF and other people, on explainable AI to really understand what's going on in these models. And I think we're at very early stages of this, but that's starting to show some of the interesting things about what kind of physics is going on in these AI models, and answer these questions about whether they are really physics-based in some form, how they've learnt that. So it's at the early stages, but that's the kind of thing that we're doing, and it needs a lot of collaboration. We're doing a lot of things, and we can't do all of them, so it needs to be collaborative and built up in the same ways we've done with our physics-based models over the years.
And I think it is important for the community. It's not just, you know, individuals or organisations or, you know, the team that are presenting it on TV. It's for everybody, isn't it? So
I'm going to be quick before handing over to Mona. I mean, I think actually the heart of this feels much broader than whether we're doing NWP or AI to me.
Yeah.
I mean, in a sense, an organisation like the Met Office, if the public aren't receiving warnings, caring, paying attention to the efforts of Mona and all the surveys done on whether people get warnings, believe them, act on them, I think that's would be the heart of my answer to this question. In some ways, whether it's NWP or AI under the hood, it feels second order to me, but I absolutely agree that all the armory of tools we use to look at the physical NWP models and what are they doing right, what are they doing wrongly, the AI models need more scrutiny through that broader lens.
Yeah, I think that we trust in you to do the right thing and manage AI responsibly, but it is that trust in science is the first and foremost important thing. And then, I daren't say the word Trump and America, but that's the worry, isn't it? It's AI algorithms and the concern of what is fed to our younger generations. So that is, you know, one of our biggest fears. So you hope that they gradually lean towards trusted sources to gather and get their information.
Yeah, very good. Yeah, certainly. Trust is hugely important. It's the first word in the Met Office strategy now, the new one. But I wanted to go back slightly to what we were talking about just now, because the trust of the public depends on the trust of the intermediary. And the trust of the intermediary is built partly from experience, but partly from the testing of the models and the demonstration that the models do the right things. And that includes things like reproducing the ED wave, reproducing the correct response of flow over a hill. There's a whole menu of test cases that are run for any new model to make sure that it reproduces what we know it should reproduce, that's based on that research that you were talking about, of the idealized cases of the reduced complexity models and reduced complexity equations and so on, including the exact answers. So I think that for NWP, certainly that has been absolutely at the core, although perhaps sometimes a little bit later in the process than maybe it should have been. For AI, I think, in some ways, I think there's a different set of problems we have to look at. Conservation momentum is sort of built into the equations, provided you use a proper solver. In NWP, conservation of momentum isn't guaranteed at all in AI. So there's a different set of things that we need to look at, and we may need some new research in order to look at what are the things that we should be looking at in an AI model to make sure that it's trustworthy.
And I guess the importance here is having scientists working alongside AI experts together. So you don't have separate teams. And my understanding at ECMW, that's very much how it works. You don't have an AI team. You have modelling teams, and you have AI people embedded within that. And I'm guessing the same at the Met Office. So it's constant. It's not developing it in isolation of the science. It's done in collaboration.
So one of the things the Met Office has done recently is we've set up a group, or the Met Office has set up a group, taking people from quite a lot of different areas. I happened to be on a part of the group initially. I was volunteered by Ben, and but really to look at or to suggest what we need to get out of AI and what we need to look at in terms of the products of AI and understand AI. And this is a group of people from different areas, forecasting and other areas throughout the Met Office, not working in AI, looking at the output of AI and how it's producing the things that we're going to produce. I mean, it's early stages. At the moment, we've been discussing, what we need to see from AI, what products they need to produce that they don't produce now, so that we can claim, well, it is representing the atmosphere, for example. Not some bunch of data. And then alongside that, going back to the trust problem, I think the Met Office has been quite conservative, perhaps in recent years, in terms of what information they're putting out, trying to reduce the hype, putting information out that you can defend and, clearly backed up by good performance and good data. And one area, of course, where Brian's been involved with a lot is with warnings. And you've got to be very careful with warnings because, if you have a high false alarm rate, you may be doing quite well. But if you have a high false alarm rate, that tends to undermine trust. And it's very difficult to get that balance right. And we're working very hard to do that, I think. But that is an element, what you produce, the accuracy of what you produce and reliability, you've got to guard very carefully and make sure that you don't undermine that reliability.
Great, thank you. Okay, hands are going up. Good. We'll start on this side of the room. So I've got two and then I'll come over to you, Martin. Yes, so microphone here. Thanks.
I've got a question about the use of the historical data. To what extent, especially doing medium-range forecasts, is the use of AI on historical data dependent on the historical data being stationary? I raise this because we have climate change, and there is renewed evidence that climate change is accelerating. It's likely to go faster. Is there a danger that the AI could be misled? For instance, when looking at the relationship between different parts of the atmosphere, that may change significantly in the future climate.
Andy, do you want to start with that?
Well, I can start with that.
Okay, Terry, you got the mic.
Yes.
Good.
I think, yes. I mean, certainly we do find with the machine learning models that they've been trained on whatever it is, 40 years of data, but just updating them with the last year of data seems to add some value. Now, in part, that may be changing of the NWP systems they have to be useful with, but in part, that may be implicitly the climate change signal. So yes, I think there's things we need to be careful of. I think observations dropping in and out seems to be less of a worry, that the reanalysis systems are more used to that. But yeah, I think I'll just revert to Terry's yes answer, I think.
Anybody else want to?
All I'd say to that is because it's a yes, then we need to be cautious on how we deploy them. And so that's very much why we're thinking about how we use these models alongside physics-based models. So until we're absolutely confident, and that may come, and that can come sooner or later, depending on what happens, we need to make sure that we remain trust.
Yeah.
That gives us from the physics-based model. So that's the strategy really, is to make sure that we are not throwing away the things that we trust straight away, that we can develop this body of evidence that fits to some threshold where we're able to trust these models.
Okay. And Brian?
Just a comment that NWP isn't entirely immune to this problem. We can't, so NWP improvements are put in if they produce better results, but they're put in if they produce better results for the vast majority of cases. When we get extreme cases, the question as to whether whether we can believe that extreme forecast is still a problem with NWP forecasts. And with the changing climate, of course, in any particular place, you're likely to get an unusual forecast more often.
Do you want to say any more than your yes?
Well, one of the things again about the AI is that was brought up recently. I think Andy might have mentioned it. That somebody else Tom mentioned it as well. The use of AI, say, observations to forecast end to end. And I think, one of the things that worries me a little bit about that is, just like for data assimilation, we have a real problem with observations over land, particularly over mountainous regions or hilly regions. If we have an observation, it's not really representative of a nearby point because of the orography. And that's going to be a real challenge. There's a real challenge in NWP. So I just wonder, how AI is going to make that leap from an observation that really doesn't represent the surrounding points, and how that goes into training the model. But perhaps somebody knows better than I do. Oh, sorry. Oh, did I? No.
Does anyone want to come back on that?
Well, can I just comment that I think it could go either way?
Well, I don't like doing this, but I agree with Brian. I think Terry's point is right. I mean, there's plenty of challenges in how we use some of this. On the other hand, we have lots of observational data at the moment, as I was saying, on the microwaves we're working on, but there's a lot of observations we have that we don't use at all in the physical NWP systems because we don't know how to. And so our AI systems are using, in our heads we can all look at a visible satellite image and interpret it. Mm-hmm. The NWP models, by and large, don't use those visible very much. And so there's extra challenges in some respects for the machine learning. In other places, I think that there's actually opportunities because we haven't been clever enough as yet to extract the value that we intuitively know is there.
Great question, thank you. So, Humphrey, do you want to go next? Then I'll do Martin and then we'll come.
So I was just going to really quickly follow up a bit on what Brian was saying about trust quite a long time ago, it seems now, but I think another element of the trust is that in the models is that if you look at the OpMet's briefing every day, they go into great efforts to understand what's going on. And if we've got a rapidly deepening cyclone, for example, they will interpret it in terms of the models that Alan was talking about and the engagement of the upper levels and the lower levels, etc. And of course, that also leads on to that if there is a rapidly deepening cyclone, they will be forensically trying to understand exactly what's going to happen to it. And so they know exactly where the areas are they need to focus on, etc., in terms of the observations. And also, obviously, ensembles is a very big part of that. So I think, just having it scrutinised by sort of scientific experts who know what's going on in the atmosphere should be an element of trust for both AI and conventional models.
Great, thank you. So no question then I'm taking from
No, it's just a comment.
No,
it's
fine.
a comment,
Thank
yeah.
you. Thanks. Martin.
Thank you. Obviously, over the last 60 years, we've seen an absolutely unbelievable improvement in weather forecasting, which is obviously due to all the various factors, observations, better science, technology. Now, I was just wondering what the panel's views are on the resilience of the whole forecasting system that we've got. Obviously, we keep going on this unidirectional improving track. But one thing that's almost like an elephant in the room to me is we're highly dependent on the observing systems. For example, just a thought, if we were to lose, for example, say the polar orbiting satellite network in a significant amount, whether it be through to hostile action or space debris or funding cuts, or whether the comms are upset by, for example, losing some of the undersea cables, is there a risk that we could even have perhaps something like that could perhaps happen quite quickly? Have we reached potentially a peak forecasting achievement now because of that? And secondly, if the models were to start becoming less reliable, we look at them now and people just take them often as gospel. Would there be the forecasting skills available being trained into modern meteorologists who could then deal with forecast models that were a lot less than perfect? So it's a big sort of question, but it just concerns me that we're sort of automatically assuming there's continuous improvement, but there could be some black swan event that could compromise our ability to forecast the weather and potentially the climate.
Yeah, good question.
have a first go. I mean, my first answer would be, yeah, absolutely, we want more observations and to keep global sharing of all the observations. That's clearly a way to keep things getting better. I think we have done some looking at that. There is some degree of resilience in the global observing network. I mean, obviously, we use satellites from Europe, from China, from Japan, from the US. If you take out any one of those, it's definitely bad. I'm not sort of saying that wouldn't be a bad thing, but there is a degree of resilience there, which is a strength of that system. So I think, both continuing to champion investment in observations, possibly even more critically in the present geopolitical situation, the model of sharing observations globally, that we all rely on observations from multiple sources. In principle, everybody's signed up to this sharing. You can imagine worlds where that sharing broke down, and I think as long as the sharing is maintained, I don't think there's a going back to the dark ages sort of, but the models would take a hit.
Anybody want to comment on the data, but also I think that human input. If things...
I'm quite positive about the resilience too, and I think we're more resilient now than we have been in the past. I mean, if you think of how we were in the 1960s or 70s, there were large parts of the world where we didn't have any observations anyway, or very, very few. Unless we lost the whole satellite constellation, I think we would be better off than we were then. And data assimilation makes it much easier to use the difficult to use, or the observations that couldn't have been used 50, 60 years ago, we can now use, and that makes it easier to keep going. In terms of the skills of the forecasters, I mean the quality of the NWP output is not constant, of course. There are still occasions when even a day ahead, the models are producing conflicting results. So I think our operational meteorologists are still kept on their toes very much, and I think the training for that is still very good. So I'm pretty confident in their ability to deal with less good NWP forecasts. Obviously, if that the end product will not be as good, but I don't see a cliff edge coming along.
Any more thoughts?
Well, one of the comments I made in my talk, actually, before NWP, weather forecasts were pretty bad. So, NWP, or AI, if it performs as well, that's got to be the route to do it. It's no good saying, well, we'll go back to what we used to call steam methods, or you just can't produce a weather forecast that matches NWP anywhere close.
I've got hands going up, but I'm going to go just behind Ian, and then we'll come forward and finish, I think, with you. I've only got 10 minutes, so question and then quick answers, please.
Okay, well, I'm not sure this is going to start with a question, more a comment. It's been mentioned by a number of you, the importance of good ideas, enthusiastic, bright young people, and their role in NWP. 3 weeks ago, in the Palace of Westminster, a new charitable trust was launched called UMaths, which is the network of university mathematics schools, of which there are about 10 in the country. These are schools focusing on 16 to 18-year-olds where they all do double maths. And the inaugural talk was given by Alex Gurko, who's the CEO of XTX Markets, a big financial modelling consortium based in London that uses AI. Now, Gurko has pump-primed this trust. He's a multi-billionaire, so he can afford to do so. But of course, he's got a vested interest in honing the training of people with the right aptitude. So my question is, what is our community, the operational centres, the Royal Meteorological Society, and through our network of university collaboration, through the Turing Institute, I'm also thinking of the Newton Institute in Cambridge, Santa Barbara, etc., etc. What are we doing to set up workshops where we're engaging with people at cutting-edge technology, where we're trying to recruit people, encourage people to go into this area? Because we're clearly playing catch-up. It would be nice to get ahead of the game, even though that could be extremely challenging.
Great question.
He said it was a comment.
Yeah. Anybody want to come back on that one? So skills for the future, I guess.
I'd just comment that the hackathons that the Met Office runs in collaboration with others, I think are an excellent way of bringing in people and enthusing them in this area. But others can probably speak to it better than I can.
Well, I think you do an ambassador scheme as well, don't you, for staff to go into to sort of colleges and no AI in that, but I think I think it's really important to communicate with students, young kids, and get that conversation. So going into schools is really important, and to kind of educate on the work that you're doing. So otherwise, it's going to become a very small group of people over time.
I mean, we talk about AI. I mean, in some ways, I worry more. Sound like Alan here. Actually, that the AI skills, I think, will be there, and the country will start churning out data scientists. I worry more about how we keep the sort of the broader underpinning understanding. You know, if everything looks sort of sexy and exciting AI, this stuff that still absolutely matters in the physical understanding. I think that's, as a community, I don't think it's a sort of burning bridge problem this year or next year, but 5, 10, 20 years, yeah.
And I think more generally, some of the curriculum work that the Royal Meteorological Society has been doing is really, really important for this, making sure that across the board, students in schools are familiar with what we do and how it's done, so that those who have the aptitude in basic maths and physics are attracted towards that aspect of what we do, but those who have the aptitudes in other areas like storytelling and the arts are attracted to the sort of thing that Mona was talking about, because that's just as important in terms of the impact of what we do as the basic sciences in terms of the accuracy of what we do.
Great, thank you. Okay, I'm going to take 2 more questions, so one here and then we'll come finish off with.
I think the first thing is a bit of a follow-up to this discussion. I was the postgrad representative of the JORC at UCL, and I understand that especially big societies and organizations, they organize hackathons, have ambassador schemes, I think that's it, we're done. But from ground zero, I can tell you, people are discouraged to join the industry because there is no path. So it's like there is a hackathon thing and everything. Then they're like, okay, we go back, we get our masters, we do our PhD, and we join the organization. But there is barely much follow through after these kind of events, after these kind of outreach schemes, where they can reach out and step through that path. The path to get into the industry remains the same. So you are conveying a message, but there is no fundamental change in the structure that is really going on. So people are still discouraged. So when, especially like what I'm seeing with my peers and those who are younger than me, they are coming and saying, this is too hard to play catch up to. And there is really a huge mindset of AI is taking away our jobs, is especially true for the younger generation. We find a lot of us are losing jobs because of AI, right? So there is a whole set of mistrust and everything that's really built up. So I guess when we are talking about things like developing AI into numerical weather forecasting, the way we brought ensemble modeling into numerical weather forecasting, I think there is a big disconnect between that and the next generation of people who would be the scientists taking it forward. So I just kind of want to understand, how do you not just talk to public about, that being another tool in the arsenal? It's just another suite of tools that we are working on. We're making explainable AI, we're doing these things. But how do you also make sure that we don't lose track of, I guess, the way people approach numerical weather modeling, climate modeling, in a sense?
Who wants to go with that one?
Yeah. Well, I may be wrong here, but I guess, one thing just to point out, meteorology, we're quite a small community. If you take the country or even the world, meteorologists, and then that includes climate science, is quite a small community. But the thing about AI and training, I think nearly all the people who are currently working in AI, in the Met Office, ECMWF and elsewhere, I doubt if they were trained in any AI while they were at university. I mean, basically, like a lot of these things, you have to kind of keep training and relearn even when you're in the job. Clearly in the future, because AI will already be out there, there'll be some education in somewhere in curricula, but nearly everybody working in it now will have had very little education in that before they actually started work, I think.
Which is why a lot of it's being done in partnership, I guess.
Yeah.
And I would envisage that as time goes on, those partnerships will result in people moving between the partners.
Yeah.
So I think that will be a mechanism.
Okay, I'm going to take one final question, just thinking of time. Hopefully your question leads to some nice short answers just to wrap us up. But we'll see how we go.
So I was thinking of kind of the theme of today as being improvements, and we've talked about observations being crucial to improvements, faster supercomputers so that we can run at higher resolution, and scientific improvements being able to model more and more complexity. Mm-hmm. In an AI world, what do those improvements come from? I'm guessing observations are still there, but what else?
Great question. So can we hear from each of you, Mona? Maybe more, I guess, in your kind of communication.
Well, quick answer. Presumably resolution is going to be one of them.
Yeah. So I would guess all the same, but also historical data, I think, will have more of a role than it has had for NWP. So mining data further back is going to be more important than it has been for NWP.
I'm just going to give a completely different context to this, but mainly I was thinking about we're obviously here talking about trust and trying to justify the progress that we're making in AI in our models. The reality is that competition is always going to be a big factor as well. So we can't afford to sort of spend too much time analysing, because unfortunately there's lots of competitors out there that are putting that information out there, and then we're going to be on a back foot. So it's a constant sort of balancing scale of moving at pace yeah, because that's the concern, is that everyone's just going to become reliant on something that actually isn't trustworthy, but they're reliant there anyway, so they're just going to stay. That's my biggest fear.
But very quick, yeah. I mean, I think in terms of their actual accuracy, I think it's data and training. I'm not sure there's a sort of a killer sort of methodological change coming next, but more data, and absolutely the sort of the wider range of products, the trust, and understanding them.
Final thoughts from you then, Ben.
Right, a very quick answer, and I'll go back to my first answer. We need clever people like you to work out how we do this. And but that's the thing. We're at a situation where we don't know a lot about all of this stuff. So we could, and this was going to be quick, wasn't it? But we there are things that we haven't explored that we could do, and we need to work out exactly what's going to go. So we need to just put the effort into working out what we're going to do with these things as we go into the future. And it could be just data, but there could be some other clever things that come along.
Great, nice way to end. Thank you. So can you join me in thanking the panel and obviously with Tom, our speakers this afternoon. That's it. Thank you.